Have you ever seen the biggest canal megaprojects on planet Earth? Stretching for hundreds of miles and massively impacting the worldwide economy, new canals keep being built at a scale bigger than the last. Today we'll tell you exactly how these impactful canal projects were made and why we would be absolutely nothing without them.
Let's investigate the next megaproject called the Ilisu Dam. Located on the Tigris River in southeastern Turkey, the project represents a major engineering and construction feat. This dam is a key component of Turkey's southeastern Anatolia project, which aims to harness the region's water resources for energy production, flood control, and irrigation. Construction of the Ilisu Dam began in 2006 and concluded in 2020. Standing 135 meters tall and stretching 1,820 meters across, the dam is a concrete-faced rock-filled structure. It has an embankment volume of 43.8 million cubic meters and creates a reservoir with a capacity of 10.4 billion cubic meters. This reservoir is essential for the dam's primary purpose of hydroelectric power generation, with an installed capacity of 1,200 megawatts from 6 Francis turbines, each producing 204 megawatts, generating about 3,833 gigawatt-hours of electricity annually. The dam's construction involves significant engineering challenges due to the region's complex geological and hydrological conditions. To manage these challenges, the Tigris River was diverted through 3 large circular diversion tunnels, each with a diameter of 12 meters and lengths ranging from 897 to 1,099 meters. This diversion was critical to keep the construction site dry, allowing for the building of the dam's foundation and ensuring a stable working environment. A key structural component of the Ilisu Dam is its sophisticated spillway system, designed to manage floodwaters efficiently. This system includes a chute and energy dissipation structures, crucial for controlling the flow of water released from the reservoir and protecting downstream areas from potential flooding. Additionally, the power plant, which houses the turbines, features state-of-the-art digital governors, shutoff valves, and ancillary systems to ensure efficient and reliable operation. Throughout its construction, the project encountered financial and logistical challenges. Initially funded by export credit agencies from Germany, Switzerland, and Austria, these backers withdrew in 2009 due to Turkey's inability to meet over 150 international environmental and social standards. Consequently, Turkey secured alternative funding through public and private bank loans, showcasing the government's commitment to completing the project despite international setbacks. The engineering work also included the construction of substantial infrastructure to support the dam. A 250-meter permanent steel girder bridge was built downstream to facilitate the transport of materials and equipment. Moreover, the project required extensive roadworks, including raising and repairing 52 kilometers of bridge to accommodate the construction needs. The powerhouse of the Ilisu Dam is equipped with 6 vertical Francis turbines, each with a capacity of 204 megawatts and 6 generators rated at 223 megavolt amperes. These components are housed in a facility designed to optimize efficiency and safety. The tail race tunnel, approximately 1,100 meters long with a maximum width of 143 meters, directs water safely away from the powerhouse, ensuring smooth operation. One of the significant engineering achievements of the Ilisu Dam is its ability to integrate advanced technology with practical construction methods. The dam's design and execution require a collaborative effort from various engineering and construction firms, employing modern techniques to address the region's unique challenges.
Gorges Dam in the United States is being expanded to nearly double its current capacity, making it one of the largest dam expansion projects in the country. The project involves raising the dam height by 131 feet, which will increase the reservoir's capacity from 42,000 acre-feet to 119 acre-feet. This expansion requires significant engineering and construction efforts, including the use of roller-compacted concrete to construct the new dam structure. The construction process begins with extensive site preparation, including the excavation of the existing dam and the construction of temporary diversion tunnels to redirect water flow. The diversion tunnels are critical to maintaining river flow and minimizing the impact on downstream ecosystems during construction. Once the site is prepared, the foundation is laid using high-strength concrete to ensure stability and durability. RCC is a type of concrete that is placed and compacted using earth-moving equipment, allowing for the rapid construction of large-scale concrete structures. The RCC is placed in layers, which are then compacted using vibratory rollers to ensure maximum density and strength. This method is highly efficient and allows for faster construction times compared to traditional concrete pouring methods. The use of RCC also reduces the amount of formwork required, as the concrete is placed in large quantities and compacted in place. This reduces the need for extensive scaffolding and supports, further speeding up the construction process. The construction of the new spillways and outlet works is also a critical component of the project, ensuring the safety and stability of the dam. The spillways are designed to handle extreme flood events, while the outlet works control the release of water for downstream use. The project also includes the installation of advanced monitoring systems to ensure the dam's safety and performance. These systems include sensors and instruments that monitor the dam's structural integrity, water levels, and environmental conditions in real time. The data collected is used to make informed decisions about dam operations and maintenance. Tehri Dam in India is one of the largest and most complex dam projects in the country. Located on the Bhagirathi River in Uttarakhand, the dam stands at a height of 853 feet and creates a reservoir with a capacity of 2.6 million acre-feet. The construction of Tehri Dam involves several significant engineering challenges, including the dam's foundation in a seismically active region and the need to manage a large volume of water. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Tehri Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 1,000 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines. Tarbela Dam in Pakistan is one of the largest earth-filled dams in the world, located on the Indus River. The dam stands at a height of 485 feet and creates a reservoir with a capacity of 11.62 million acre-feet. The construction of Tarbela Dam involved several significant engineering challenges, including the need to manage a large volume of water and the dam's foundation in a seismically active region. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Tarbela Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 3,478 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines.
It's time for a much more monumental project, the Grand Inga Dam. in the Democratic Republic of Congo. Proposed as the largest hydropower project in the world, the Grand Inga Dam has the potential to generate a staggering 40 to 70 gigawatts. It's more than twice the capacity of the Three Gorges Dam. The Inga Falls, situated about 225 kilometers southwest of Kinshasa, the capital of DRC, is already home to the smaller Inga 1 and Inga 2 hydropower stations. The project envisions a series of 7 interconnected dams, with Inga III serving as the starting phase. Initially planned at 4,800 megawatts, the design of Inga III was later expanded to 11,000 megawatts. This has increased the total estimated cost of the project to $18 billion, including $4 billion for transmission lines. The Grand Inga Dam would divert the Congo River through the Bundy Valley, creating a vast reservoir to generate power. The unique combination of high water volume, vertical drop, and velocity in the region makes it ideal for hydropower. Each of the proposed 7 power stations would have independent ownership, enabling phased development. The Inga 3 phase will provide electricity to major stakeholders: 5,000 megawatts to South Africa, 3,000 megawatts to Nigeria, 1,300 megawatts to DRC mining companies, and the remainder to the national utility. This dam could boost industrialization in Africa by providing affordable energy for manufacturing, mining, and urban centers. It is also expected to create jobs, improve access to electricity in rural areas, and reduce reliance on fossil fuels, contributing to global climate goals. In 2018, the DRC government partnered with Chinese and Spanish firms for technical studies and environmental impact assessments. This phase aims to balance the energy generation with socio-economic and environmental considerations. The project has faced significant delays due to financing hurdles, requiring extensive resource mobilization. Additionally, agreements with nations through which transmission lines pass, such as Nigeria and South Africa, need re-evaluation. Several countries and international organizations, including South Africa and the World Bank, have expressed interest in funding and partnering on the project. However, political instability and logistical challenges have delayed progress. The Grand Inga Dam holds transformative potential for Africa, but must overcome significant obstacles to realize its vision of powering a continent. Once completed, the dam could supply clean, renewable energy across Africa, adding to the economic growth and addressing chronic energy shortages. But just wait until you hear about one of China's most expensive projects, the South-North Water Transfer Project, with $79 billion already spent. This Chinese mega-project addresses the critical water scarcity issues in the country by transferring water from the resource-rich south to the drought-prone north. The project includes 3 main routes: the eastern, central, and western lines. The eastern and central routes are operational, supplying water to cities like Beijing, Tianjin, and Shandong province. The western route, still in planning, aims to divert water from the upper reaches of the Yangtze River through the Tibetan Plateau to northern provinces. Spanning over 2,000 kilometers, the project required constructing massive canals, tunnels, pumping stations, and reservoirs. The central route alone diverts 9.5 billion cubic meters of water annually and passes through engineering feats like the Danjiangkou Reservoir. The project is complex and uses TBMs for tunneling, hydraulic drilling machines for dam construction, and high-capacity pumps for testing canal systems. Precision-guided excavators handle massive earth-moving tasks, while automated concrete pouring systems ensure uniformity in canal linings. Advanced monitoring devices are employed to maintain water flow integrity. Due to the topography of the Yangtze Plain and the North China Plain, pumping stations will be employed. They'll raise water from the Yangtze to the Yellow River crossing. Farther north, the water will flow downhill in an aqueduct. The project has brought much-needed water to arid regions, supporting agriculture, industry, and urban growth. By securing water resources for northern economic hubs in China, the project sustains industrial output, urbanization, and population growth. It also reduces reliance on overexploited groundwater, preventing further environmental degradation. Despite its successes, the project has faced significant challenges. Relocation of over 330,000 people to create reservoirs sparked social concerns. Additionally, managing pollution along the routes remains a priority, as water quality directly impacts urban and agricultural usage. Scientists have expressed concerns that the project could increase water evaporation loss. The exact amount of evaporation loss is not known, but it may improve in the future as more water is transferred and the flow rate increases. With more than 40 billion cubic meters of water transferred annually, the project is a lifeline for many regions. Its completion in 2050 will mark a significant milestone in global water management, demonstrating how large-scale infrastructure can address critical resource challenges.
But what about a massive dam megaproject? For that, we have to travel to the Ohio River, where the Olmsted Locks and Dam project is located. This monumental undertaking, designed to replace aging infrastructure and modernize the waterway system, is crucial for the transportation of billions of dollars worth of goods annually across Central States. This project, which officially completed in 2018 after over 30 years of planning and construction, spans across the river and involved an extraordinary financial investment of approximately $3 billion. The construction required the sustained effort of hundreds of engineers, technicians, and laborers over several decades, underscoring the project's scale and complexity. The Olmsted project replaced two older and less efficient facilities, locks and dams 52 and 53, which had become increasingly unreliable, causing significant delays in river traffic and logistical inefficiencies. The new structure consists of a navigational pass and two parallel 110-foot by 200-foot locks. This setup significantly eases the river traffic, allowing for the smooth passage of approximately 90 million tons of cargo yearly. One of the notable challenges of the Olmsted Locks and Dam was its innovative construction method, specifically the use of in-the-wet technology. Unlike traditional dry dock methods, this technique involves assembling large modular sections of the dam on land, then floating them to their installation site on the river. The total amount of concrete used in the dam's construction would be enough to pave a sidewalk stretching from New York to San Francisco. A special feature of the Olmsted Locks and Dam is its resilience to seismic activity. The region is near the New Madrid fault line, and as such, the structure was designed to withstand significant earthquakes, ensuring the long-term stability and safety of this critical infrastructure. The project's importance extends beyond just its immediate functionality. By improving the reliability and efficiency of the Ohio River as a navigational channel, the Olmsted Locks and Dam also bolsters the economic viability of river transportation, which is significantly more fuel efficient and environmentally friendly compared to road and rail transport.
Next, it's time to talk about the Itaipu Dam project, located on the borders between Brazil and Paraguay. This colossal structure harnesses the power of the Paraná River, generating a staggering 14,000 megawatts of electricity. The dam plays a vital role in the energy supply of both countries, providing approximately 15% of Brazil's electricity needs and 75% of Paraguay's. Construction of the Itaipu Dam began in 1975 and was completed in 1984, involving a massive workforce and significant engineering challenges. The dam itself is about 4.8 miles long and 643 feet high, creating a reservoir that covers an area of 521 square miles. The reservoir, known as the Itaipu Reservoir, has a total storage capacity of 29 billion cubic meters of water. One of the most impressive aspects of the Itaipu Dam is its power generation capability. The dam houses 20 generating units, each with a generating capacity of 700 megawatts. These units utilize Kaplan turbines, which are highly efficient for the varying water flow rates of the Paraná River. The power generated is transmitted through high-voltage lines to both Brazil and Paraguay, playing a crucial role in the economic and industrial development of the region. Environmental and social considerations were critical and integral to the project. The construction of the dam necessitated the relocation of around 40,000 people and significant ecological changes, including the creation of the Itaipu Biological Reserve to protect wildlife. The project also involved extensive reforestation efforts and the establishment of fish hatcheries to mitigate the environmental impact. Managed jointly by Brazil and Paraguay through the Itaipu binational entity, it stands as a testament of what can be achieved through collaboration.
But how about a barrier megaproject that will protect an entire city? Venice, a city renowned for its unique architecture and intricate waterways, has been facing an existential threat from flooding due to rising sea levels and sinking foundations. In response, Italy embarked on one of the most ambitious and technically complex engineering projects in Europe, the Venice Flood Barrier, officially known as the MOSE project. Initiated in 2003, the project comprises a series of 78 mobile underwater gates designed to temporarily isolate the Venetian lagoon from the Adriatic Sea during high tides. Spanning 3 inlets that connect the lagoon to the sea, each gate measures 20 meters wide and weighs up to 300 tons. When not in use, these gates rest in caissons on the seafloor filled with water. During high tides, air is pumped into these caissons, causing the gates to rise and block the incoming water. The technical challenges of constructing such a system were immense. Engineers had to develop new materials and methods to ensure the gates could withstand the harsh marine environment, including building special corrosion-resistant barriers that could endure for decades. The project also involved massive dredging operations to lay the foundations of the gates, moving millions of cubic meters of seabed. But besides those challenges, delays and cost overruns were frequent as well, pushing the project's completion date several times. The initial budget ballooned from an estimated $1.6 billion to an eventual total of $5.7 billion, making it one of the most expensive megaprojects in Europe. Unlike conventional dams or levees, the Venice Flood Barrier is designed to be both invisible and temporary, appearing only when needed to protect the historic city.
Let's talk about the Keyask Hydroelectric Project, located on the Nelson River in Canada. This project has a total capacity of 695 megawatts and is designed to harness the power of the Nelson River to generate renewable energy. The primary structure of the Keyask Hydroelectric Project is the generating station, which consists of a concrete powerhouse housing 7 turbine generator units. The Keyask project includes 7 dams with a combined length of nearly 24 kilometers and 2 large dikes designed to control water flow and create the necessary head for power generation. The powerhouse and spillway structure were constructed using large quantities of reinforced concrete, with the total concrete volume used in the project exceeding 700,000 cubic meters. The turbine and generator units at Keyask are Kaplan turbines, chosen for their efficiency in harnessing the variable flow of the Nelson River. The installation process included the careful alignment of the turbine shafts and the precise calibration of the generator units to ensure optimal performance. Next up, let's discuss the Glen Canyon Dam that's located on the Colorado River in Arizona. Constructed between 1956 and 1966, the dam was designed to provide water storage, flood control, and hydroelectric power generation for the southwestern United States. The dam created Lake Powell, one of the largest man-made reservoirs in the country, which extends into southern Utah. The construction of the Glen Canyon Dam was a massive undertaking that required extensive planning, innovation, and the overcoming of significant engineering challenges. The dam is a concrete arch-gravity structure standing 710 feet high and 1,560 feet long. It was designed to harness the power of the Colorado River while also providing a stable water supply for agricultural, industrial, and urban use in the region. One of the critical challenges during the construction of the Glen Canyon Dam was the remote location. The site, located in a remote area of the Colorado Plateau, was difficult to access, requiring the construction of roads, bridges, and other infrastructure to support the transport of materials and workers. The dam's construction also involved building the Glen Canyon Bridge, a steel arch bridge that spans 1,271 feet across the canyon, providing essential access to both sides of the construction site. To manage the Colorado River's flow during construction, engineers had to divert the river through tunnels carved into the canyon walls. 2 diversion tunnels, each with a diameter of 41 feet, were excavated through the sandstone bedrock on either side of the river. These tunnels, lined with concrete, allowed the river to bypass the construction site, ensuring that the dam could be built in a dry environment. The foundation of the dam required extensive preparation. Workers excavated the riverbeds down to solid bedrock and ensured a stable foundation for the massive concrete structure. The dam's foundation is key to its stability, allowing it to bear the immense pressure exerted by the reservoir. The concrete used in the dam was placed in blocks, each measuring about 50 feet square and 7.5 feet high. The dam was constructed in a series of these blocks, which were keyed and grounded together to form a solid monolithic structure. The dam's power plant, located at the base of the structure, houses 8 hydroelectric turbines that generate up to 1,320 megawatts of electricity. This power generation capacity has been vital in supporting the electric grid of the southwestern United States. The power plant is also equipped with a series of penstocks, large pipes that carry water from the reservoir to the turbines, allowing for the controlled water release and energy production. It's time to travel over to Turkey next for a record-breaking dam mega project. The Yusufeli Dam stands at 275 meters tall, making it the highest dam located in Turkey and the 5th highest of its kind worldwide. Construction on the Yusufeli Dam began in 2013 and culminated in 2022, transforming the landscape and significantly boosting Turkey's energy capacity. The dam is designed as a double-curvature concrete arch structure. Its crest length extends 490 meters, and the maximum crest elevation reaches 715 meters. This immense structure created a reservoir covering 33.63 square kilometers with a total storage capacity of around 2.2 billion cubic meters. Such a massive reservoir required the precise engineering and use of approximately 220 tons of steel for the gates and 3,800 tons of steel for the penstocks. One of the critical components of the Yusufeli Dam is its power generation capability. The dam houses a 558-megawatt hydroelectric power plant, equipped with 3 vertical axis Francis turbine units, each rated at 186 megawatts. These turbines are designed to operate with a head of 191 meters and discharge of 107 cubic meters per second. The power plant's annual electricity production capacity is approximately 1.9 billion kilowatt hours. The electricity generated is evacuated through a 380 kilovolt switchyard and transmission line, integrating it into Turkey's national grid. The construction of the Yusufeli Dam faced numerous geological challenges due to the complex and fractured formations of the Çorum Valley. Extensive geotechnical studies were conducted to understand the site conditions and plan the construction accordingly. Digital 3D geotechnical models were employed to manage the design and construction phases, providing a real-time data and enabling adjustments as excavation progressed. This innovative approach ensured the stability and safety of the dam structure. In addition to the dam and power plant, the project included the construction of significant ancillary infrastructure. 4 balanced cantilever viaducts were built, including the 644-meter-long Tehri Viaduct and the 695-meter-long Yusufeli Viaduct. Moreover, the project involved constructing 110 kilometers of new roads, 45 tunnels, 22 bridges, and 92 culverts, all designed to support the dam's operation and enhance regional connectivity. The construction process required sophisticated equipment and techniques. The dam's height and curvature demanded precise engineering and the use of advanced construction machinery. Tower cranes with varying capacities, including one 12-ton 280 ECH tower crane, 2 10-ton 200 ECH tower cranes, and 4 6-ton 154 ECH tower cranes were utilized to handle the heavy lifting and placement of materials.
Next up, we have to talk about the Grand Coulee Dam, an engineering masterpiece and one of the largest infrastructure projects in United States history. Built during the Great Depression, its construction spanned from 1933 to 1942, offering much-needed employment and economic stimulus to the region. Located on the Columbia River in Washington state, the dam is a cornerstone of American hydropower, irrigation, and water management. The dam was conceived as part of President Franklin D. Roosevelt's New Deal, aimed at boosting economic recovery through large infrastructure projects. Its dual purpose was to generate hydroelectric power and irrigate vast tracts of arid land. This was all about transforming the Columbia River Basin into a fertile agricultural region. With a length of 1.6 kilometers and a height of 168 meters, it is one of the largest concrete structures in the world. Today, it produces 6,800 megawatts of electricity, supplying power to 2 million homes annually. The reservoir of the dam, Franklin D. Roosevelt Lake, irrigates over 600,000 acres of farmland, driving agricultural productivity. Additionally, the power plants in the dam supply electricity to millions, facilitating industrial growth and regional development. The Grand Coulee Dam stretches 1,592 meters across the Columbia River and rises 168 meters from its granite foundation. It required a staggering 11.9 million cubic yards of concrete, 3 times that used in the Hoover Dam. Its thickness ranges from 30 feet at the top to 500 feet at the base. The dam houses 4 power plants, including the left and right power plants, each equipped with 9 generators, rated at 125 megawatts each. A later addition, the third power plant, features 6 generators, 3 of which boast a capacity of 805 megawatts each, making it a powerhouse of energy production. The total generating capacity of the dam is 6,809 megawatts, sufficient to power millions of homes and industries. Building the Grand Coulee Dam required innovative techniques, including individual penstocks, giant pipes up to 40 feet in diameter, to carry water to the generators. A labor force of over 8,000 workers at its peak tackled harsh weather conditions and complex engineering challenges. The spillway, spanning 1,300 feet, was designed to handle massive water flows, protecting the structure from flooding. The Grand Coulee Dam has not only transformed the Columbia River Basin into an agricultural haven, but also ensured energy security for the Pacific Northwest. Its contribution to irrigation, flood control, and recreation has solidified its status as an engineering marvel. Today, the dam attracts tourists worldwide and offers educational tours. There's an annual laser light show that celebrates its monumental history and technological significance.
Sardar Sarovar Dam in India is one of the largest and most complex dam projects in the country. Located on the Narmada River in Gujarat, the dam stands at a height of 535 feet and creates a reservoir with a capacity of 7.7 million acre-feet. The construction of Sardar Sarovar Dam involves several significant engineering challenges, including the need to manage a large volume of water and the dam's foundation in a seismically active region. The construction process began with extensive site preparation, including the excavation of the dam foundation and the construction of diversion tunnels to redirect the river's flow. The foundation was reinforced with high-strength concrete and rock anchors to ensure stability and durability. The dam itself was constructed using earth and rock fill, with a central clay core to provide impermeability. The construction of the diversion tunnels involved the use of tunnel boring machines to excavate the tunnels through the surrounding mountains. These machines are capable of cutting through hard rock and soil, creating a smooth tunnel lining that minimizes water leakage. The TBMs were equipped with advanced sensors and monitoring systems to ensure precise alignment and minimize the risk of collapse. Once the foundation and diversion tunnels were complete, the dam's main structure was built using a combination of earth, rock, and concrete. The materials were placed in layers and compacted using heavy machinery to ensure maximum density and strength. The clay core was constructed in sections, with each section carefully compacted and tested for impermeability. The Sardar Sarovar Dam project also included the construction of a power plant at the base of the dam. This plant houses multiple hydroelectric turbines capable of generating 1,450 megawatts of electricity. The turbines are driven by water released from the reservoir, which flows through large penstocks and turns the turbine blades. The electricity generated is transmitted to the national grid through high-voltage transmission lines.
The Waima Community Dam in New Zealand is a significant project aimed at providing a reliable water supply for the Tasman region. The construction of this earth-filled dam involved complex engineering techniques to address the unique geological and environmental challenges of the site. The dam, standing 174 feet tall and 1,210 feet long, is designed to store approximately 13 billion gallons of water. The construction process began with extensive site preparation, including the excavation of a large foundation trench to ensure a stable base for the dam. This involved removing unsuitable materials and replacing them with engineered fill. The foundation was then treated with a combination of grouting and drainage systems to manage groundwater and prevent seepage. These measures are critical for maintaining the dam's structural integrity and ensuring long-term stability. The dam's core is constructed using impervious clay, which acts as a barrier to prevent water from seeping through the structure. This clay core is flanked by zones of carefully compacted earthfill, providing support and stability. The construction of these zones involved precise layering and compaction techniques to ensure that each layer met the required specifications for density and moisture content. This meticulous process helps to prevent settlements and maintain the dam's structural integrity over time. To enhance the dam's safety, a robust spillway system was designed to handle potential overflow during periods of heavy rainfall. The spillway consists of a concrete chute and energy dissipation structures, which are designed to safely convey excess water downstream without causing erosion or damage to the dam. The design and construction of the spillway required careful planning and execution, taking into account the potential impacts of extreme weather events and climate change. The construction of the Waima Community Dam also included the developments of extensive monitoring and control systems. These systems involved the installation of piezometers, inclinometers, and other instrumentation to monitor the dam's performance and detect any potential issues early. This real-time data is crucial for the ongoing management and maintenance of the dam, ensuring that it operates safely and effectively. The Oroville Dam in California, United States, is the tallest dam in the country at 770 feet, underwent significant reconstruction following the spillway failure in 2017. The reconstruction project, completed in 2019, involved extensive engineering and construction efforts to restore the dam's safety and functionality. The reconstruction focused on the main and emergency spillways, both of which were damaged during the 2017 incident. The project began with the demolition of the damaged sections, followed by the excavation and preparation of the foundation. This involved the removal of unstable materials and the installation of drainage systems to manage groundwater and prevent future erosion. The main spillway was reconstructed using high-strength roller-compacted concrete, a technique that involves placing and compacting layers of concrete using heavy rollers. This method provides a durable and erosion-resistant surface capable of withstanding high water flows. The RCC was placed in layers, each approximately 12 inches thick, and compacted to achieve the required density and strength. The emergency spillway was reinforced with a new concrete weir and an extensive network of concrete walls and slabs, designed to control water flow and prevent erosion. The construction of these structures required precise formwork and concrete placement techniques, ensuring that the new spillway could handle extreme flood events. One of the significant challenges during the reconstruction was managing the continued operation of the dam and reservoir. This required careful coordination and planning, including the use of temporary spillways and water management systems to ensure the safety of downstream communities. The project also involved extensive monitoring and testing to verify the performance of the new structures and ensure compliance with regulatory standards. The Oroville Dam reconstruction project demonstrates the application of advanced engineering and construction techniques to address critical infrastructure needs. The project restores the dam's safety and functionality, ensuring the reliable management of California's water resources. The successful completion of this complex and challenging project showcases the capabilities of modern civil engineering to solve significant infrastructure challenges.
But just wait until you hear about one of Russia's most iconic megaprojects, The Krasnoyarsk Dam. Built on the Yenisei River near Krasnoyarsk in Siberia, this massive hydroelectric dam is a landmark of Soviet-era engineering and a vital part of power grids in Russia. Completed in 1972, the Krasnoyarsk Dam is a gravity dam that stretches 1065 meters across the Yenisei River and stands 124 meters tall. With an installed capacity of 6,000 megawatts, it generates enough electricity to power industries and homes across the Krasnoyarsk region and beyond. The dam is particularly crucial for supplying energy to the Krasnoyarsk aluminum smelter, one of the largest in the world. The Krasnoyarsk Dam features a 600-meter wide spillway capable of discharging 2,000 cubic meters of water per second. The reservoir of the dam, known as the Krasnoyarsk Reservoir or Krasnoyarsk Sea, stretches over 2,000 kilometers and holds a staggering 73.3 billion cubic meters of water. One of the standout features of the dam is its ship lift, a unique engineering solution that allows vessels to bypass the dam by moving over its massive structure. This lift, one of the largest of its kind, facilitates transportation along the Yenisei River, connecting Siberia to the Arctic Ocean. The creation of the Krasnoyarsk Reservoir flooded vast areas of forest and farmland, displacing thousands of people. It also disrupted local ecosystems and altered the natural flow of the river. However, the dam provides critical flood control, protecting downstream communities from seasonal flooding. The Krasnoyarsk Dam plays a key role in supporting the industrial economy of Russia. Its reliable energy output ensures the smooth operation of heavy industries like aluminium production, which are essential for both domestic use and export. The dam also serves as a significant source of employment and regional development. Despite its benefits, the Krasnoyarsk Dam has faced criticism for its environmental impact and the social costs of its construction. Nevertheless, it remains a symbol of Soviet-era ambition and a testament to the power of hydropower in driving economic growth.
Welcome to the Muskrat Falls project, a colossal hydroelectric power station on the lower Churchill River in Labrador. Did you know that the Muskrat Falls project spans over 100 square kilometers? The project harnesses the power of water, generating up to 824 megawatts of electricity, enough to light up over 500,000 homes. Construction kicked off in 2013 and, amidst various challenges, wrapped up in late 2020. The scale of this endeavor is staggering, with a final cost soaring to approximately 12.7 billion Canadian dollars. Originally estimated at 7.4 billion, the financial scope ballooned due to unforeseen geological challenges and logistical complexities. The construction of the dam itself is a feat to behold. The main dam, made from over 2.2 million cubic meters of concrete, stretches across 32 meters in height and an impressive 432 meters in length. The project utilized innovative construction techniques, such as the extensive use of large-scale prefabricated modules to speed up the construction process and reduce the environmental impact. The harsh weather conditions of Labrador, with freezing temperatures and heavy snow, tested the mettle of every worker on site. Muskrat Falls also integrates cutting-edge technology with a series of 204-kilometer transmission lines, known as the Labrador Island Link, which connect the power generated from the falls to the population centers. This technological marvel includes software that allows the power flow to be adjusted in real time, optimizing energy distribution based on current demand and supply conditions. Muskrat Falls is connected to the island of Newfoundland by a subsea cable spanning nearly 30 kilometers across the seabed of the Strait of Belle Isle. This is one of the longest subsea electricity cables in the world, a little shorter than the length of Manhattan.
Next, we have to talk about one of the biggest dams constructed in China, the Longtan Dam. Located on the Hongshui River in Guangxi Province, this $4.2 billion project is one of the tallest roller-compacted concrete dams in the world, standing at 216.5 meters. The Longtan Dam was built to generate hydroelectric power, improve flood control, and enhance navigation along the river. Completed in 2009, the dam stands 216.5 meters tall and stretches 849 meters in length. Its 6,426 MW of capacity makes it one of the largest hydropower stations in China, supplying clean energy to millions of households and industries. Constructed using roller-compacted concrete, the Longtan Dam features a unique design that enhances its strength and efficiency. The reservoir capacity is a staggering 27.3 billion cubic meters, with an active capacity of 16.2 billion cubic meters. The gross head of the dam measures 179 meters, enabling its power station to achieve a colossal installed capacity of 6,426 MW. This includes 7 turbines, each with a capacity of 700 MW, along with 2 additional turbines added in a later phase. The electricity generated by Longtan is sold to China's Southern Power Grid, meeting the power demands of millions while reducing reliance on fossil fuels. The dam also plays a critical role in flood control, irrigation, and water supply management, contributing to regional stability and development. Furthermore, its presence aligns with the commitment of China to renewable energy, significantly reducing carbon emissions. While the dam provides significant benefits, it also comes with environmental costs. Its construction displaced over 8,000 people and submerged 300 square kilometers of land, including forests and farmland. Efforts have been made to relocate affected communities and mitigate ecological damage. One of the notable features of the dam is its ship lift, which allows vessels to bypass the dam and continue along the river. This has improved trade and transportation in the region, boosting local economies. The Longtan Dam faced challenges during its construction, including geological issues and public opposition. However, its successful completion has cemented its role as a vital component of the energy and water management strategy implemented by China. Today, the Longtan Dam has become a popular tourist destination, drawing visitors to marvel at its sheer scale and engineering brilliance.
We can't overlook the massive Klamath River project. With a price tag of $450 million, this project involves removing 4 hydroelectric dams to restore natural fish migration patterns and improve water quality. For over a century, these dams have blocked vital fish habitats, and the removal is set to be completed by the end of 2024. This will open up 400 miles of river for species like Chinook salmon and steelhead trout. Let's dive into the engineering behind this transformative project. The 4 dams planned for removal are known as the Lower Klamath Project. They include the J.C. Boyle, Copco No. 1, Copco No. 2, and Iron Gate dams. These dams were originally built for hydroelectric power generation, but they've also severely disrupted natural water flow and fish migration for decades. So how do you remove dams that stood for a century? At J.C. Boyle Dam, an existing drain that was originally built to divert water during the construction of the dam will be used to drain the reservoir. Concrete step logs currently blocking this drain will be blasted open to allow the water to flow through. Once the reservoir is drained, workers will begin demolishing the dam structure itself. Meanwhile, at Copco No. 1, engineers will drill a new tunnel through the base of the dam. This tunnel will act as a controlled release point for water. The demolition crews will use drilling and blasting techniques to dismantle Copco No. 2 and Iron Gate Dam. The goal of this project isn't just about removing dams, it's about restoring an entire ecosystem. The Klamath River project is the largest dam removal project in U.S. history. It's part of a growing movement to rethink how we manage natural resources, prioritizing ecosystem health and sustainability over industrial infrastructure. Projects like this set a powerful example for future ecological restoration efforts. Over 76,000 cubic meters of concrete and 2,000 tons of steel will be removed. Nearly 1 million cubic meters of material will be excavated to return the river to its natural state.
The Sayano-Shushenskaya Dam in Russia is one of the most iconic hydropower stations in the world. Located on the Yenisei River in Siberia, this $1.2 billion project stands at an impressive 242 meters, making it one of the tallest dams ever. Stretching across a length of 1066 meters, this arch-gravity dam is a critical component of hydropower infrastructure in Russia. The dam was built to utilize the immense flow of the Yenisei River for power generation and flood control. The reservoir, with a storage capacity of 31.3 cubic kilometers, provides consistent water flow for year-round electricity production. Designed to withstand earthquakes up to 8 on the Richter scale, the dam showcases exceptional structural resilience, even earning a place in the Guinness Book of World Records for its unique construction. The Sayano-Shushenskaya power station has an installed capacity of 6,400 megawatts and generates approximately 23,500 GWh of electricity annually. The 10 turbines in the dam, each rated at 640 megawatts, operate with incredible efficiency. The reservoir also ensures steady water flow during peak energy demand, adding to the energy security of Russia. In 2009, the dam faced one of its greatest challenges. A catastrophic turbine malfunction caused a massive flood in the turbine hall, resulting in 75 fatalities and extensive structural damage. Power generation was severely reduced, and the accident raised concerns about operational safety. Following the tragedy, an intensive $1 billion rehabilitation and modernization program was undertaken between 2010 and 2014. This effort restored the full capacity of the dam and incorporated advanced monitoring and safety systems to prevent future incidents. The dam plays a pivotal role in reducing the reliance of Russia on fossil fuels, contributing significantly to its renewable energy output. It also supports regional agriculture and industry by providing reliable water management. Despite its immense scale, the dam's integration into the Sayano-Shushensky Nature Reserve reflects a balance between energy production and environmental preservation. Let's move over to the Three Gorges Dam in China, towering over the Yangtze River in Hubei province. Completed in 2006 after 17 years of construction, it is the largest hydropower project in the world. Built at a cost of approximately $28 billion, it serves multiple purposes, including flood control, hydroelectric power generation, and improving river navigation. First proposed in the early 20th century, the dam was envisioned as a solution to the Yangtze River's devastating floods. The river, spanning thousands of kilometers, is prone to flooding that has historically claimed thousands of lives and caused immense economic damage. Construction began in 1994 with the primary goal of reducing flood risks and generating clean energy. This dam symbolizes modernity and progress preferred by China. Stretching 2,335 meters across and standing 181 meters tall, the dam's scale is monumental. Its reservoir extends 660 kilometers upstream, creating a water storage capacity of 22 billion cubic meters. The dam operates 34 massive turbines, producing a combined output of 22.5 gigawatts, enough to power millions of homes annually. This energy production reduces reliance on coal, significantly cutting greenhouse gas emissions. The construction involved massive earth-moving operations and precise placement of reinforced concrete. Workers used diversion canals to redirect the Yangtze's flow, enabling the dam's foundation to be laid. The dam has 5-tier ship locks at each end that allow vessels up to 1,000 tons to pass. It also has a ship lift that can raise cargo ships up to 1,800 tons. While the dam provides immense benefits, it has come with steep costs. Over 1.2 million residents were displaced to make way for the reservoir, impacting local communities. Environmental concerns include disrupted sediment flow, which affects aquatic ecosystems and downstream biodiversity. The altered river flow has also led to increased landslides and erosion along the edges of the reservoir. Designed to mitigate flooding, the dam regulates water flow by holding rainwater in its reservoir during the rainy season. However, Critics argue that its storage capacity, while vast, can only manage 9% of extreme floodwaters. In severe conditions, the limits of the dam are exposed, leading to debates about its long-term effectiveness. Despite its success, the dam has been criticized for increasing seismic activity and causing landslides due to the immense weight of the reservoir. Concerns about water quality and sedimentation have also emerged, highlighting the need for ongoing management and research. Than the Robert Bourassa, the largest dam and hydro project in northern Quebec. But what about the Atlantropa, one of the most ambitious and controversial engineering concepts ever imagined in the Strait of Gibraltar? Proposed by German architect Hermann Sergel in the 1920s, the project aimed to drain large parts of the Mediterranean Sea by constructing massive dams at strategic points. The idea was to reclaim vast amounts of land for European settlement, generate immense hydroelectric power, and create a peaceful solution to overpopulation in Europe. During the 1920s and 1930s, Europe faced soaring population growth, rising energy demands, and several geopolitical tensions over land and resources. Sergel's concept, named Atlantropa, proposed to address these challenges by merging Europe and Africa into a single economic and cultural bloc called Eurafrica. He wanted to transform the Mediterranean basin into fertile land, connecting the continents with railways and canals, while using dams to generate hydroelectric power. The project revolved around three massive dams. Strait of Gibraltar, a colossal dam spanning 13 kilometers with a height of 300 to 900 meters, is designed to separate the Mediterranean from the Atlantic Ocean. Dardanelles Strait, another dam to block the connection of the Mediterranean to the Black Sea. Then, Sicily, Tunisia, a 150-kilometer dam to split the Mediterranean into western and eastern basins, allowing different water levels for optimal land reclamation. The drained areas would reveal 700,000 square kilometers of land, doubling the size of Germany. The dams would also act as hydroelectric power stations, providing renewable energy for the region. The reclaimed land was envisioned as fertile plains for agriculture and urban development, easing the strain of overpopulation in Europe. The scale of the Atlantropa project was unprecedented. The Strait of Gibraltar Dam alone would have required engineering feats still unachieved today. The construction would involve multiple smaller dams, acting as steps to manage water pressure, inspired by projects like the Zuiderzee works in the Netherlands. The plan also included building canals to maintain trade routes for cities like Venice and Cairo, which would have been stranded inland by the lowered sea levels. The estimated cost of this project was astronomical, over $1 trillion in today's currency. The technology, resources, and international cooperation needed were far beyond what was available. Critics highlighted safety concerns, such as the catastrophic consequences of dam failure and the environmental impact of altering an entire ecosystem. The colonialist undertones of the project also sparked opposition, particularly from African nations wary of European dominance. Despite its grand vision, Atlantropa never materialized. Sergel spent his life advocating for the project, but skepticism and World War II sidelined his dream. After his death in 1952, the idea faded into obscurity. Today, Atlantropa stands as a symbol of human ambition and the complex balance between innovation, environmental stewardship, and social responsibility. In the case of the Coastal Virginia Offshore Wind Project, the entire effort hinges on the careful coordination of marine construction in open ocean conditions, which demands a completely different approach than land-based renewable energy developments. The process begins long before any steel touches the water with an exhaustive geotechnical survey of the seabed. Crews deploy specialized survey vessels equipped with multi-beam sonar, sub-bottom profilers, and cone penetration testing equipment to map the subsurface layers in fine detail. This information dictates the exact placement and design of the turbine foundations, as the Atlantic sandy sediments can vary greatly in density and composition over relatively short distances. Once the optimal positions are confirmed, the installation phase for the foundations begins. Jack-up installation vessels, capable of lifting themselves out of the water on massive legs for stability, are mobilized to the site. Each turbine foundation, typically a monopile in this particular project scale, is fabricated onshore, transported by barge, and then driven deep into the seabed using hydraulic impact hammers. To prevent scouring around these foundations from constant wave and current action, a protective layer of rock armor is placed at the base, delivered by fall pipe vessels that can accurately drop stone in rough seas. Following the establishment of foundations, transition pieces are installed. These are cylindrical structures fitted over the top of the monopiles, designed to provide a precise connection interface for the turbine towers. Inside these transition pieces, workers fit ladders, cable hang-offs, and landing platforms for future maintenance access. All bolted connections are pre-tensioned to exact specifications, and every weld is inspected both visually and with non-destructive testing to ensure long-term durability in the harsh marine environment. Parallel to the structural work, cable laying operations take place. High voltage export cables, manufactured in continuous lengths, are loaded onto specialized cable laying vessels equipped with large turntables. From the offshore site to the onshore landing point, the cable is carefully placed into pre-dredged trenches and then buried using either jetting or ploughing systems to protect it from anchors and fishing gear. Near shore, horizontal directional drilling is used to pull the cable through to a land-based transition station without disturbing the beach or nearshore ecosystem. The turbine assembly process is one of the most visually striking parts of the project. Tower sections, nacelles, and rotor blades are transported offshore and installed in a carefully choreographed sequence. Tower sections are lifted and bolted together first, followed by the placement of the nacelle, the housing for the generator and gearbox, and finally, the massive blades, each of which can be well over 100 meters in length. Given the limited weather windows for safe lifts, every component's arrival and installation is timed to the hour. Back on shore, the grid connection infrastructure is constructed. This includes the installation of transformers, switchgear, and protection systems to integrate the offshore generation into the regional power network. Once testing and commissioning are complete, the wind farm begins full operation, delivering clean energy while being monitored from an onshore control center that can track turbine performance, detect anomalies, and even adjust blade pitch remotely to maximize efficiency and minimize wear. Buried deep in the mountains of southeastern Tibet, there's a river that carves through some of the most rugged terrain on Earth, twisting and falling through a gorge deeper than the Grand Canyon, with more raw untapped power than almost any river in the world. This is the Yarlung Tsangpo, and right near the remote county of Medog, China is planning something that could change the entire energy equation of Asia. A hydroelectric project so enormous, so ambitious, and so politically charged that it's hard to believe it's even real. Now, what makes this project so unique isn't just the size, although that alone is staggering. The Medog hydropower project is being planned to generate more electricity than even the Three Gorges Dam, which is already the largest power station on Earth. If completed, it would produce somewhere in the ballpark of 60 gigawatts, enough to power entire nations, by harnessing the incredible natural drop of the river as it plunges through the world's deepest canyon. And the wild thing is, it's not some slow, meandering descent. The Yarlung Tsangpo crashes down thousands of meters in a short span, creating a perfect scenario for ultra-high head hydroelectricity. But the challenges here are just as intense as the engineering dream. First off, the terrain is basically vertical. This region is remote, landslide prone, and regularly battered by extreme weather, not to mention earthquakes. Transporting materials and equipment up here means cutting through one of the least accessible areas in China, which in itself becomes a construction project the size of a mega project. And then there's the environmental question. Medog sits in one of the most biodiverse and fragile ecosystems in the Himalayas. Dam the river here, and you don't just affect a local valley, you impact everything downstream, from Indian states to Bangladesh, who rely on this same water flowing through their farmlands. Which brings us to the other layer, geopolitics. India sees the Yarlung Tsangpo as the upper reach of the Brahmaputra River, which feeds millions of people downstream. So when China talks about putting a giant dam across this section, it sets off alarms. Water security, strategic control, ecological disruption, it's all wrapped into one enormous and highly sensitive project. Yet for China, the prize is irresistible. A clean energy source of that magnitude, generated inside its own borders, could be a cornerstone for reaching its carbon neutrality goals and reducing its reliance on coal. And beyond all the politics and environmental concerns, there's the engineering itself. Imagine building tunnels and intake systems through rock that's constantly shifting, where just getting workers to the site takes hours over winding cliffside roads, and every drop of rain could trigger a mudslide. It's not just about pouring concrete and installing turbines, it's about reshaping an entire mountainside, building under conditions where nature constantly pushes back. Stretching across the southern portion of Florida, the Everglades represents one of the most unique and delicate ecosystems in North America. And the series of restoration projects aimed at rehabilitating this landscape stand as some of the most ambitious hydrological engineering efforts ever undertaken in the United States. These projects collectively focus on undoing decades of human alteration that disrupted natural water flows, severely impacted wildlife habitats, and degraded water quality. The engineering challenges associated with these efforts are vast, involving large-scale earth moving, hydrological modelling, structural water control features, and long-term adaptive management. At the heart of the restoration initiative is the re-establishment of natural sheet flow, which refers to the slow, shallow movement of water southward across the Everglades flat terrain. Historically, this flow was interrupted by the construction of levees, canals, and pumping stations that redirected water for urban and agricultural uses. To address this, engineers have designed and constructed massive flow equalization basins, stormwater treatment areas, and pump stations that carefully mimic the timing and volume of historical water deliveries. One of the key undertakings involved the removal or modification of hundreds of miles of canals and levees, such as the partial deconstruction of the Miami Canal and the rerouting of flow into restored wetland corridors. This work required precise excavation and reshaping of land to ensure that water could once again disperse evenly and slowly across the landscape. Earth-moving operations were executed with amphibious excavators and low ground pressure tracked vehicles to reduce soil compaction and environmental disruption. In areas where water storage was a major constraint, large reservoirs were constructed, some exceeding tens of thousands of acre-feet in capacity. These reservoirs are lined and equipped with high-volume inflow and outflow structures controlled by gated spillways and electrically operated valves. Their purpose is to capture stormwater during wet seasons and release it in a controlled manner during dry periods, mimicking natural hydrological cycles. Adjacent to these reservoirs are extensive stormwater treatment areas composed of shallow, vegetated cells that use aquatic plants like cattails and submerged vegetation to remove excess phosphorus and other nutrients. The restoration projects also necessitated the construction of extensive culvert networks and bridges to allow water to pass underneath roadways, particularly along major east-west transportation corridors such as Tamiami Trail. These structures were designed to accommodate large volumes of slow-moving water without impeding traffic or causing structural undermining. The foundations of these bridges were pile-driven deep into stable substrata, and the superstructures were built using pre-stressed concrete beams capable of withstanding Florida's corrosive and humid environment. Monitoring infrastructure is integrated throughout the system, including flow gauges, water quality sensors, and automated telemetry stations. Data collected from these devices feed into centralized control systems that allow engineers and hydrologists to make real-time adjustments to water releases, ensuring ecological targets are met. The adaptive management strategy also includes provisions for ongoing modifications as performance data accumulates over years of operation. In the highlands of Ethiopia, right near the border with Sudan, a wall of concrete now stretches across the Blue Nile, a dam so massive that it's already reshaping not just the country's energy supply, but the politics of an entire region. This is the Grand Ethiopian Renaissance Dam, often shortened to GERD, and it's one of the most controversial and ambitious infrastructure projects in Africa's modern history. From a purely engineering standpoint, GERD is enormous. The main dam structure stands over 140 meters tall and spans nearly 2 kilometers across the Nile. Behind it, a reservoir capable of holding more than 70 billion cubic meters of water is slowly taking shape, making it one of the largest man-made lakes in Africa. And the hydroelectric potential is just as impressive. When fully operational, GERD is expected to generate over 6,000 megawatts of electricity. That's more than doubling Ethiopia's entire power capacity and turning the country into a potential electricity exporter for the whole East African region. But building this dam was never just about power. For Ethiopia, it's a matter of sovereignty and development. For decades, the country has relied on foreign energy imports and struggled to bring electricity to its rural population. GERD is seen as the key to unlocking long-term economic growth, creating jobs, supporting industry, and expanding access to power across millions of homes. It's a project that has been paid for largely through domestic funding, with the government encouraging citizens to invest in national bonds and support the construction financially and symbolically. That national pride, though, is matched by rising tensions downstream. Both Sudan and Egypt depend heavily on the Nile for irrigation, agriculture, and drinking water, and Egypt in particular has historically viewed the river as a lifeline. For generations, water treaties dating back to colonial times guaranteed Egypt a dominant share of the Nile's flow. Now, with Ethiopia holding back massive volumes of water behind a new dam, those old agreements are being tested. The fear from Cairo is that GERD could reduce the flow of water downstream, especially during the filling period of the reservoir, which could hurt Egyptian agriculture and water security. Ethiopia argues that the dam will actually help stabilize flow, reduce flooding, and benefit all three countries in the long term. But so far, years of negotiations haven't produced a final deal, and the disagreement has created real diplomatic friction, with threats, warnings, and political standoffs becoming more frequent. On the ground though, GERD is nearing completion. The first turbines are already spinning, and power is being delivered to the grid. Construction has taken over a decade, involving thousands of workers and a coordinated effort to bring in materials and equipment through difficult terrain. The logistics alone were staggering, given the remote location and the scale of the build. Whether GERD becomes a unifying symbol of African development or a long-term source of conflict depends on what happens next. Cooperation is still possible, but so is escalation. But next up, we have to talk about the Seikan Dam in Canada, a critical project located on the Peace River in northeastern British Columbia. Located just 14 kilometers southwest of Fort St. John, this project is the latest addition to the network of dams in British Columbia. Soon, it will become the fourth largest hydroelectric producer in the province. When operational in 2025, Site C will generate 1,100 megawatts of electricity, supplying enough clean energy to power approximately 45,000 homes annually. The project is intended to provide a reliable and affordable source of clean electricity for more than 100 years. It will also stabilize energy costs and support industries like mining and forestry. The idea for Site C emerged in the 1970s, following the successful completion of the W.A.C. Bennett Dam and Peace Canyon Dam, also on the Peace River. Initially delayed due to environmental concerns and fluctuating energy demands, the project was revived in the early 2000s. Construction finally began in 2015, after contentious debates over its necessity and impact on the local ecosystem and communities. Site C is a $16 billion initiative employing cutting-edge engineering and construction techniques. The dam features an earth-fill structure standing 60 meters tall and spanning over 1,050 meters across the river. The construction involves extensive diversion tunnels to redirect the river during the building process. Colossal machinery is employed for the installation of large-scale turbines capable of generating 4,600 GWh of electricity annually. The project also includes a spillway and powerhouse, where water flow is converted into clean energy. Advanced geotechnical stabilization methods ensure the resilience of the structure, even in challenging seismic conditions. While Site C promises sustainable energy, it has faced significant opposition. The dam's reservoir will flood 5,500 hectares of agricultural land, destroying fertile soil and impacting wildlife habitats. It is responsible for putting indigenous burial grounds, traditional hunting and fishing areas, and habitats for more than 100 species vulnerable to extinction. This has drawn criticism from environmentalists and Treaty 8 First Nations, who argue that the project violates their rights and disrupts traditional practices. Site C has further been affected by delays, budget increases, and legal challenges from opponents. The pandemic further disrupted construction schedules, adding to the complexities of the project. Despite these setbacks, the government remains committed to completing the dam, with an operational target of 2025. The Site C Dam is the most expensive public infrastructure project in the history of British Columbia. However, it has a much lower capacity. Let's travel over to the Himalayan Mega Dam in China, a colossal structure nestled in the towering peaks of Tibet. Built on the Yarlung Changpo River and often called the Everest of Rivers, this $100 billion project is set to redefine hydropower in the region. Its location in one of the most rugged and remote regions in the world adds to its engineering complexity and significance. The dam is part of China's efforts to achieve carbon neutrality by 2060. It's expected to generate enough clean electricity to power the UK for a year. The Yarlung Changpo features the steepest descent, with its waters plunging over 2,000 meters within a 100-kilometer stretch. This geological phenomenon creates a unique opportunity for hydroelectric generation, but it also presents formidable engineering challenges. The gorge of the river, carved into ancient granite bedrock, is 3 times deeper than the Grand Canyon. This makes it a natural wonder and a high-risk construction zone. The Himalayan region is no stranger to catastrophic flooding. Historical evidence shows that glacially dammed lakes have failed in the past, unleashing devastating outburst floods. Such events have dramatically reshaped the landscape and affected human settlements. These risks loom large over the dam project, as landslides or earthquakes could compromise the structural integrity of the dam. This is indeed a serious threat to downstream communities in India and Bangladesh. Construction on this colossal project began in 2015, and the completion date has not been announced yet. The dam employs state-of-the-art run-of-river hydroelectric systems, reducing the environmental impact by avoiding large reservoirs. Advanced geospatial mapping was used to identify stable construction zones, and cutting-edge tunnel boring machines carved pathways through the rugged terrain. The dam stands at an impressive 315 meters, capable of generating 43.8 million kilowatts of electricity annually. Its power output eclipses that of the Three Gorges Dam, making it the largest hydropower station in the world. Beyond its technical achievements, the Himalayan Mega Dam has far-reaching geopolitical implications. As the Yarlung Po flows into India and then into Bangladesh, the dam gives China significant control over water resources critical to millions. This has heightened tensions, with fears that reduced river flow could increase water scarcity in downstream nations. Some experts warn of a potential water war in a region already filled with geopolitical complexities. While the dam promises clean energy, it threatens to disrupt delicate ecosystems and the biodiversity of the river. Downstream communities risk losing vital aquatic resources, similar to the environmental toll seen on the Mekong River from previous Chinese dam projects. Moreover, the river holds profound spiritual significance for Tibetans, symbolizing a sacred goddess. Altering its flow has led to resistance from local communities, who view the project as a violation of their cultural heritage. Despite its challenges, the Himalayan Mega Dam highlights the potential for innovative engineering solutions. By adopting sustainable practices and engaging in international cooperation, there is hope for mitigating environmental and geopolitical risks.
It's time to move on to one of the biggest pipeline megaprojects in the world, called the Nord Stream gas pipeline. Stretching beneath the Baltic Sea to connect Russia with Germany, this strategic pipeline, operational since November 2011, spans approximately 124 kilometers, making it one of the longest offshore gas pipelines in the world. With a total project cost estimated at 8.8 billion euros, the Nord Stream has the capacity to transport up to 55 billion cubic meters of natural gas annually, playing a crucial role in ensuring energy security and diversification of supply routes in Europe. Constructed using state-of-the-art technology, the pipeline comprises two parallel lines, each made from tens of thousands of steel pipes welded together on board specialized vessels. These pipes, coated for corrosion resistance, were laid on the seabed by some of the world's most advanced laying ships, navigating through challenging marine conditions. Despite its technical achievements, Nord Stream has been mired in controversy. Critics argue that it increases European dependency on Russian gas, posing geopolitical risks. Environmental groups have also raised concerns about the potential impacts on the Baltic Sea's delicate ecosystem. Yet, proponents highlight its contribution to energy security and lower carbon emissions compared to coal and oil. Let's transition to another underwater project that is connecting cities, called the Busan-Gyeonggi Fixed Link. Spanning an impressive length of 8.2 kilometers, this fixed link connects the bustling city of Busan with the scenic island of Gyeonggi in South Korea, serving as a vital artery that significantly reduces travel time. Constructed at a cost of approximately $800 million, the project was completed in 2010 after 5 years of relentless work. The fixed link is a hybrid structure, comprising both bridges and underwater tunnels, ingeniously designed to navigate the challenges posed by the area's deep waters and heavy marine traffic. The centerpiece of this engineering feat is a 3.7-kilometer immersed tunnel, one of the longest of its kind in the world, which plunges beneath the sea to allow ships to pass unimpeded above. Despite its successes, the project was not without its challenges. Environmental concerns were raised regarding the impact on the marine ecosystem, leading to stringent measures being implemented to mitigate damage. Financial obstacles also loomed large, with debates on the project's cost-effectiveness and the burden on public resources sparking rigorous discussions. Now it's time for a different type of underwater project, and for that we have to travel to the United States, where the Lake Mead Intake No. 3 tackles the critical issue of water scarcity. This monumental project, costing an impressive $817 million, was driven by the urgent need to secure a reliable water supply for Las Vegas, a city that depends heavily on the waters of Lake Mead. Initiated in 2008 and completed in 2015, the project involved drilling a 3-mile-long tunnel beneath Lake Mead, one of the largest man-made lakes in the United States. This was no ordinary task. It required the use of a 1,500-ton tunnel boring machine, cutting through the earth at depths reaching 600 feet below the lake's surface. The purpose? to construct a new intake capable of drawing water from the lake's depths, ensuring access to clean water even as lake levels fluctuated perilously low due to prolonged drought conditions. The construction of intake number 3 was not just about securing a water source, it was about innovating for the future. Engineers and workers faced the daunting challenge of working in an environment where temperatures soared, and the risk of flooding within the tunnel was a constant threat. It's time to travel back to Norway for another incredible underwater project. The Oslofjord Tunnel serves as a vital link beneath the waters of the Oslofjord, connecting the regions of Østfold and Buskerud. Completed in 2000 at a cost of around $84 million, this underwater tunnel significantly reduces travel time between Oslo and the cities on the fjord's eastern side, fostering economic and social integration in the area. Spanning 7,306 meters, it is one of the longest underwater road tunnels in Norway, with a descent reaching 134 meters below sea level at its deepest point. The construction of the Oslofjord Tunnel was a complex engineering challenge, requiring the use of a drill and blast technique to carve through the rock beneath the fjord. Safety features within the tunnel, such as comprehensive ventilation systems and emergency exits, are paramount, reflecting Norway's commitment to road safety. Its construction underscores the balance between technological advancement and environmental stewardship, embodying Norway's approach to sustainable development. Now let's move to an underwater project that does not yet exist, and that would break many records if it was being constructed. The transatlantic tunnel, connecting New York to London, is a testament to human ambition and engineering prowess. But the next underwater project is going to be a lot more feasible. The Gibraltar Strait Tunnel seeks to connect Europe and Africa, specifically Spain to Morocco, through a 14-kilometer underwater rail tunnel. This endeavor not only aims to bridge two continents, but also to significantly enhance economic and cultural exchanges between them. The project, with an estimated cost that could exceed $20 billion, is a testament to the potential of modern engineering to overcome geographical barriers. Construction of such a tunnel presents formidable challenges, from the deep waters of the Strait of Gibraltar, with depths up to 900 meters, to the seismic activity in the region. The proposed tunnel would be among the world's longest underwater tunnels, dwarfing existing ones in both ambition and technical complexity. Engineers are considering innovative boring techniques and special materials to ensure the tunnel's integrity and safety, taking lessons from other underwater projects like the Channel Tunnel between France and the United Kingdom. But Japan is arguably even better at constructing underwater tunnels, because they constructed the much longer Seikan Tunnel. Stretching 54 kilometers, with a staggering 23 kilometers lying under the seabed, it connects the islands of Honshu and Hokkaido, piercing through the Tsugaru Strait. Completed in 1988 after nearly 2 decades of construction, the tunnel resolves the overcoming of geographical isolation and enhances connectivity. With an overall cost of approximately $3.6 billion, the Seikan Tunnel's construction presented formidable hurdles, including dealing with the seismic volatility of the region. Our next underwater project is the only underwater research laboratory in the world, and it's called the Aquarius Reef Base, located in the United States. Anchored 62 feet or 19 meters below the surface near Key Largo, this remarkable facility offers scientists a unique, aquatic vantage point for studying marine biology, underwater physiology, and the impacts of climate change on coral reefs. Established in 1986, Aquarius has facilitated groundbreaking research by allowing researchers to live and work in the ocean's depths for extended periods. The 400-square-foot habitat is equipped with living quarters, laboratories, and communication systems, enabling teams to dive deeper into their research without the daily decompression requirements that limit bottom time for surface divers. Being the only underwater lab in operation, the Aquarius Reef Base exemplifies human ingenuity in pursuit of scientific knowledge, turning the ocean's alien environment into a classroom. While that tunnel might be long, it's time to visit a tunnel that's over 10 times as long. The Channel Tunnel, an engineering feat that bridged the UK and France beneath the English Channel, stands as a symbol of European unity and technological ambition. Completed in 1994 at a cost of £12 billion, this project was one of the most significant engineering projects of the 20th century. Spanning 50.45 kilometers, with 37.9 kilometers beneath the sea, the Channel Tunnel holds the record for the longest undersea portion of any tunnel in the world. The construction involved the use of 11 tunnel boring machines to carve through the chalk marl beneath the seabed. This Herculean task required unprecedented coordination between British and French construction teams. The tunnel comprises 3 separate tubes, 2 for rail traffic and a smaller service tunnel that acts as an emergency escape route. The use of precast concrete linings to reinforce the tunnel walls was a critical component of the construction strategy, ensuring the tunnel's durability and safety. Today, the Channel Tunnel is a vital link for commerce and travel between the UK and continental Europe, facilitating the seamless transit of millions of passengers and tons of freight annually. But the underwater megaprojects can get much longer than that. The Baltic Pipe project was completed in 2022 at a cost of approximately 1.6 billion euros, and it stretches over 900 kilometers, forging a direct link between Norway's gas fields and Poland, with passages through Denmark. Its primary aim is to diversify energy sources and reduce Central and Eastern European countries' dependence on Russian gas, showcasing a pivotal shift towards sustainable and secure energy supplies. The construction of the Baltic Pipe involved laying underwater pipelines across the North Sea and the Baltic Sea, a challenging endeavor that required advanced engineering techniques. Specialized ships were deployed to lay the pipes on the seabed, ensuring minimal disruption to commercial navigation routes. This project is notable not just for its engineering achievements, but also for its role in enhancing political cooperation among European nations. By providing a stable, reliable source of natural gas, the Baltic Pipe supports Europe's goals of energy independence and sustainability, relying less on Russia's Nord Stream pipe. It's time to visit the United Kingdom, where a tunnel is being constructed for an ambitious purpose. The Thames Tideway tunnel aims to tackle London's over a century-old sewage system problem. Officially initiated in 2016 with an estimated completion by 2025, this massive undertaking is designed to prevent millions of tons of untreated sewage from entering the Thames River each year. Stretching over 25 kilometers and delving up to 65 meters below the river, the tunnel is a critical component of modernizing London's sewage disposal and treatment capabilities. Costing approximately £4.9 billion, the project is not just an engineering marvel, but also a significant environmental initiative. By intercepting overflow from existing Victorian sewers, the tunnel will ensure that the Thames remains cleaner and more vibrant for future generations. Despite its environmental benefits, the Thames Tideway Tunnel has faced controversy, particularly regarding its financial impact on residents through increased water bills. Crossing the North Sea, it's time to visit Norway for a massive underwater megaproject. Norway's Coastal Highway project is an unparalleled infrastructure endeavor aimed at revolutionizing travel along the country's rugged western coast. With an estimated cost of $40 billion, this ambitious project seeks to eliminate the need for 7 ferry crossings by connecting the cities of Kristiansand in the south to Trondheim in the north through a continuous, ferry-free highway. Spanning over 100 kilometers, it involves the construction of bridges, tunnels, and causeways designed to navigate the challenging Norwegian underwater terrain and weather conditions. A highlight of the project is the proposed construction of the world's longest and deepest submerged floating tunnel, a feat of engineering that exemplifies Norway's innovative approach to overcoming geographical obstacles. This tunnel alone, part of the route across the Sognefjord, is expected to stretch 3.7 kilometers in length and reach depths of up to 392 meters below sea level. Scheduled for completion in 2050, the Coastal Highway project not only aims to significantly reduce travel time across the western coast, but also to boost economic growth and connectivity in remote regions. Let's travel to the Netherlands next for one of the most impressive underwater projects on the list so far. The Western Scheldt Tunnel, completed in 2003 at a cost of approximately €750 million, is not just a passage but a lifeline, connecting the regions of Zeeuws-Vlaanderen and South Beveland, and significantly reducing travel time in the area. Spanning an impressive 6.6 kilometers, the Western Scheldt Tunnel holds the title of the longest tunnel in the Netherlands. Constructed using the immersed tube method, it consists of segments that were meticulously built on land and then submerged and connected beneath the Scheldt River. This construction approach required precision and innovation, including the use of GPS technology to ensure exact alignment of the tunnel sections. But how about a tunnel that has been connecting 2 countries for over 2 decades? Let's check out the Øresund Tunnel, which is part of the Øresund link that connects Denmark and Sweden, facilitating unprecedented connectivity between the two countries since its completion in 2000. This project, with a total cost of around €4 billion for the entire Øresund link, includes a bridge, an artificial island, and the tunnel itself, showcasing a blend of engineering ingenuity and cooperation across borders. Stretching 4 kilometers beneath the Øresund Strait, the tunnel complements the 8-kilometer bridge to form a comprehensive transport route. The construction of the tunnel employed the cut-and-cover method, where a trench was excavated on the seabed, and prefabricated tunnel sections were then lowered into place. The Øresund Tunnel has significantly reduced travel time between Denmark and Sweden, bolstering economic ties and cultural exchange. The next project on our list is a tunnel that's connecting two major countries, the Fehmarn Belt Fixed Link. This ambitious project, with an estimated cost of €7.4 billion, is not just another infrastructure endeavor. It's a bold leap towards uniting regions and enhancing mobility in Europe by connecting Germany and Denmark. Spanning approximately 18 kilometers, it's poised to become the world's longest immersed tunnel, designed for both rail and road traffic. The construction employs the use of specially designed ships to lay sections of the tunnel on the seabed, a method that underscores the innovative spirit of this undertaking. The tunnel comprises 79 individual segments, each meticulously fabricated off-site, showcasing the meticulous planning and precision that underpin this colossal project. The planned completion date for this project is unknown, but they're aiming to open it somewhere in 2029. While underwater tunnels are usually used for mobility, Canada is utilizing them for something else with their Seymour Capilano water filtration project. Nestled in the verdant landscapes of British Columbia, Canada, the tunnel is an engineering marvel designed to ensure the provision of clean, safe drinking water to the Vancouver metropolitan area. This project is distinguished by its expansive network of tunnels, stretching over 7.1 kilometers, which serve as conduits for transferring water between the Seymour Reservoir and the Capilano Reservoir. Constructed at a cost of over $600 million Canadian dollars, the project underscores the critical importance of sustainable water management in urban planning. The construction process showcased a blend of traditional tunneling methods and modern technological innovations. 2 massive tunnel boring machines were deployed, each weighing over 1,000 tons, carving through the mountainous terrain with precision. The project became operational in May 2010, and ever since it has been a vital part of the region. A country that can obviously not be missing from this list is China, who has their own fair share of underwater megaprojects. Let's dive into the Hong Kong-Zhuhai-Macau Bridge Tunnel. Overcoming the physical and economic divide between Hong Kong and Zhuhai, this project was completed in October 2018, consisting of a series of bridges and tunnels spanning approximately 55 kilometers, making it one of the longest sea-crossing structures in the world. With a budget exceeding $18.8 billion, the project is designed to facilitate the flow of people and goods, strengthening connectivity and economic integration within the Pearl River Delta region. At the heart of this colossal structure is a 6.7-kilometer underwater tunnel, descending up to 40 meters below the sea level, seamlessly connecting 2 artificial islands. This tunnel was a critical solution to avoid disrupting the busy maritime lanes in the Pearl River estuary. The construction of the tunnels required innovative engineering techniques, including the use of immersed tube tunnel methods for the underwater sections. While the next underwater project may not be as big, the Poseidon Underwater Hotel is just as remarkable. This groundbreaking project, aiming to be nestled in the clear turquoise waters of Fiji, extends the frontier of hospitality into the aquatic realm. The hotel is designed to feature 25 suites, each encased in a 70mm thick transparent acrylic shell, providing 360-degree views of the vibrant marine ecosystem. With an estimated construction cost of $105 million, the hotel's ambition is not just to provide luxury, but to pioneer in eco-friendly engineering. The structure is planned to be anchored at a depth of 40 meters below the sea level, covering an area of approximately 5,000 square meters. It's time to visit Norway, which has constructed a crucial underwater project called the Ormen Lange gas pipeline. Spanning an impressive 1,200 kilometers, it connects the Ormen Lange field in the Norwegian Sea to the United Kingdom, specifically to the processing plant at Nyhamna, Norway. Commissioned in 2007, This pipeline plays a crucial role in securing energy supplies in the region, marking a significant achievement in the field of energy infrastructure. Constructed at a cost of over $10 billion, the Ormen Lange gas pipeline's engineering required innovative solutions to navigate the challenging deep water conditions of the Norwegian Sea, including depths of up to 100 meters. This project also stood out for its environmental and technical challenges, particularly the need to minimize impacts on the delicate marine ecosystem and address the harsh conditions found in the North Sea. Let's travel to Turkey for the first project, where the Marmara Rail Tunnel was launched back in 2013, linking the European and Asian parts of Istanbul. Spanning approximately 76.3 kilometers in total length, with 13.6 kilometers running under the sea, the Marmara project was developed with a budget of $4 billion. The construction of the Marmara Tunnel involved the deployment of some of the most advanced technologies and machinery in the field of civil engineering. A pivotal element of this project was the use of immersed tube tunnel technology, which involves the fabrication of tunnel sections on land, subsequently towed to the site, and meticulously lowered onto a prepared trench on the seabed. However, one of the most significant hurdles was the archaeological discoveries made during the excavation phases. Istanbul's rich history was laid bare as the project unearthed a treasure trove of historical artifacts, including Byzantine ships, which required meticulous archaeological examination. The United States also has constructed some really impressive underwater megaprojects, such as the Chesapeake Bay Bridge Tunnel, stretching over the waters of the Chesapeake Bay to connect Virginia's eastern shore with the mainland. Opened in 1964 and expanded over the years, this 23-mile marvel is not just a bridge, but a series of bridges, tunnels, and artificial islands. Constructed at a cost of approximately $200 million at its inception, with subsequent expansions adding to the investment, the Bay Tunnel stands as a testament to human ingenuity and overcoming geographical challenges. The structure includes two 1-mile tunnels that dive beneath the bay, allowing ships to pass unimpeded above, while miles of low-lying trestle bridges provide breathtaking views of the surrounding waters. The use of the bridge-tunnel combination was a pioneering approach, providing a direct, uninterrupted flow of traffic across the bay and demonstrating a harmonious blend of functionality and environmental sensitivity.
High in the Colorado Front Range, nestled against the backdrop of the Rocky Mountains, the construction of the Chimney Hollow Reservoir unfolds as a feat of modern engineering designed to address long-term water storage and supply challenges. This reservoir, when completed, will serve as a crucial component of the Windy Gap Firming Project, tasked with ensuring a reliable water supply to over a dozen municipalities and water districts. The reservoir is not a natural formation, but a carefully engineered off-channel storage solution, meaning it is not built directly on a river, but instead captures and stores water piped from elsewhere, in this case, from the Colorado River, through the existing Windy Gap infrastructure. The site preparation phase began with intensive geotechnical surveys to confirm the structural integrity of the valley where the dam would be located. Crews cleared vegetation, regraded access routes, and constructed temporary diversion channels to handle stormwater runoff during the construction process. An essential early task involved excavating unsuitable soil and rock from the dam footprint, replacing it with engineered fill to provide a uniform foundation capable of supporting the massive weight of the structure. The dam itself is a rockfill embankment design with a central clay core, a choice made for its flexibility and impermeability. The clay core serves as the primary barrier to water seepage and is compacted in thin lifts using specialized rollers to ensure density and homogeneity. This core is flanked by transition zones of sand and gravel, which in turn are bordered by larger rockfill shells. These outer shells provide structural stability and protect the inner components from erosion and seismic activity. The rock used for the dam is sourced from on-site quarrying operations, which reduces the environmental footprint and transportation costs. A significant engineering challenge in this project involves the hydraulic structures that regulate the inflow and outflow of water. An intake tower, constructed with reinforced concrete, rises vertically near the upstream face of the dam, equipped with multiple inlets at varying elevations to allow selective withdrawal of water depending on quality and temperature needs. Connected to this intake is an outlet tunnel bored through bedrock, reinforced with steel liner sections and anchored against hydrostatic forces. In parallel, crews are constructing an upstream reservoir rim lined with a composite geomembrane to minimize seepage losses. This liner is protected with layers of cushion material and rock ballast to guard against mechanical damage. The dam crest will support an access road and monitoring equipment, including piezometers and inclinometers embedded within the dam body to detect any movement or internal pressure changes over time. Environmental mitigation measures are ongoing throughout the project. These include fish passage improvements elsewhere in the watershed, wetland restoration and extensive erosion control using sediment basins, wattles, and hydroseeding on disturbed slopes. All construction activities are sequenced with seasonal weather patterns in mind, avoiding critical wildlife periods and minimizing impacts during spring runoff and winter freeze-thaw cycles. Restoration efforts on the Colorado Big Thompson project have involved a multi-decade sequence of upgrades, structural reinforcements, and modernization of both above-ground and subterranean components across a vast regional network. Spanning trans-mountain diversion tunnels, hydropower facilities, pumping plants, canals, reservoirs, and dam structures, the complexity of renovating this mid-20th century water infrastructure lies not only in the scale of its components, but in the critical, continuous water delivery it must maintain throughout every construction and retrofit phase. At the core of the project is the Alva B. Adams Tunnel, which transports water beneath the Continental Divide. The original tunnel lining, constructed from cast-in-place concrete following drill and blast excavation, has faced decades of hydrostatic pressure, abrasive sediment flow, and thermal expansion stress. Modern inspection robots, equipped with LiDAR and ultrasonic probes, traverse the interior to map defects. Where cracking, voids, or liner degradation is identified, hydrodemolition methods strip the compromised material. Layers of fiber-reinforced shotcrete are then applied, sometimes with embedded stainless mesh or steel lattice reinforcement, to restore structural strength and flow profile. Major valve chambers and penstocks connecting to the hydropower stations have also seen extensive retrofitting. Aging butterfly and cone valves, once manually operated and fabricated from cast iron, are being replaced with stainless steel equivalents that feature automated controls integrated into SCADA systems. Valve replacement requires dewatering and confined space access, necessitating bypass piping and upstream cofferdam installation. In some sites, penstock joints are strengthened with carbon fiber wraps and anchored against slope instability through the use of ground anchors drilled into bedrock. Reservoir and dam structures have undergone re-evaluation to comply with contemporary safety standards, especially in the context of seismic vulnerability and climate-induced hydrological extremes. Earth-filled dams, such as those at Carter Lake and Horsetooth Reservoir, have been subject to slope stability assessments using modern finite element analysis. Remediation includes flattening embankment slopes, adding chimney drains constructed with well-graded filter sands, and recompacting fill zones to increase seismic resilience. Some dam crests have been raised by several feet to increase freeboard, while auxiliary spillways are being constructed with concrete chute structures lined with energy-dissipating blocks to handle probable maximum flood events. Instrumentation throughout the system has transitioned from analog to digital. Remote monitoring nodes, including piezometers, extensometers, and pressure transducers, feed real-time data into a centralized operations center. This allows for predictive maintenance, dynamic reservoir management, and early warning during extreme weather events. Redundant telemetry paths ensure system integrity even during partial outages. The canal network and siphons responsible for water delivery to Eastern Plains users also required attention. Siphons built from riveted steel pipe were either relined with cured-in-place polymer systems or entirely replaced using slip lining techniques. Open canals were reshaped with laser grading and then lined with concrete or synthetic geomembrane to reduce infiltration losses and improve flow velocity. Turnouts and flow control gates were fitted with actuators and sensors, reducing labor demands and improving response time during flow adjustments. Throughout the renovation, work was heavily constrained by seasonal water demand and the operational requirement to maintain delivery. Construction windows were short, often confined to late fall and winter when irrigation demand was lowest. Shutdowns were planned months in advance and executed with minute-by-minute coordination between contractors and operations personnel. In many cases, redundant systems or emergency bypasses were fabricated in advance to allow full system function while isolated sections were taken offline. What makes the gross reservoir expansion particularly notable from an engineering standpoint is not just the increase in storage volume, but the sheer complexity involved in raising a massive concrete dam in situ, while maintaining safety, environmental compliance, and hydrologic function. The project revolves around the elevation of the existing dam structure, originally built in the 1950s, to nearly double the reservoir's capacity, thereby enhancing the long-term water reliability for the Denver metropolitan area. The core of the expansion involves adding height to the dam crest using roller-compacted concrete, a technique chosen for its rapid placement and high strength. Before this process could begin, detailed geotechnical surveys and structural assessments were conducted on the existing dam face and foundation. Crews cleaned, scarified, and roughened the old concrete surface to ensure bond integrity with the new layers. Then, a construction staging area was established below the dam, including mixing plants, conveyors, and cooling systems to support uninterrupted RCC placement. This material was delivered in massive batches and placed in lifts, each typically less than 1 foot thick, compacted with vibratory rollers before the next layer was added. One of the critical challenges was maintaining structural monolithicity across old and new concrete interfaces. Water stop systems were embedded at construction joints to prevent seepage, and grout enrichment zones were applied in transition areas to ensure full load transfer. To handle the thermal stresses that come with such a large volume of concrete, the RCC mix was designed with low cement content and placed during cooler times of day, sometimes even at night, to minimize temperature gradients and avoid cracking. Adjacent infrastructure required significant adaptation. The reservoir's spillway had to be realigned and enlarged to accommodate increased discharge capacity under extreme storm conditions. This involved the construction of a new chute and energy dissipation basin, built with high durability reinforced concrete and designed using computational fluid dynamics models to optimize flow control and prevent downstream erosion. Additionally, the intake structure, located at depth near the dam base, was retrofitted with extended vertical gates and enhanced debris exclusion systems to accommodate the new water levels and future sediment inflows. Access improvements were essential to facilitate the scale of the operation. Narrow, winding mountain roads were widened and reinforced with retaining walls, geogrid stabilized embankments, and asphalt overlays capable of supporting heavy construction traffic. Equipment staging zones were built into switchbacks, while dust suppression and runoff controls, such as sediment traps and hydro-mulching, were continuously deployed to limit ecological impact in the forested watershed. Environmental compliance was managed through a comprehensive mitigation strategy, including stream restoration projects, fish habitat enhancements downstream, and continuous turbidity monitoring in discharge channels. Construction timing was carefully coordinated with wildlife breeding seasons and precipitation patterns to minimize disruption to sensitive ecosystems. To ensure structural integrity and operational control over the long term, the project also introduced new instrumentation across the dam body and reservoir basin. This includes piezometers, joint meters, and laser scanning targets embedded within the new RCC layers and surrounding terrain. These instruments provide real-time data on stress distributions, deflection, seepage, and uplift pressures, feeding into a central monitoring platform overseen by dam safety engineers. Every aspect of the Gordie Howe International Bridge's construction showcases the intricate interplay between transnational coordination, advanced structural engineering, and logistical execution at a scale rarely attempted in modern infrastructure. Spanning the Detroit River and connecting Detroit, Michigan with Windsor, Ontario, this cable-stayed bridge is designed to support massive volumes of commercial and passenger traffic, requiring not only the longest main span of any cable-stayed bridge in North America, but also a level of precision in its execution that leaves no room for error. The construction began with extensive geotechnical investigations on both riverbanks. Drilling rigs bored deep into the soil and bedrock to analyze subsurface conditions, as the design called for massive pylon foundations to be embedded securely below the frost line and into competent strata capable of bearing immense vertical and lateral loads. These foundations were formed using deep caisson shafts, reinforced with high-density steel cages and tremie concrete placed underwater to displace slurry and avoid cold joints. Each tower foundation supports a pylon rising hundreds of feet above the river, built incrementally using a climbing formwork system that allowed for the continuous casting of reinforced concrete without the need for external scaffolding. The bridge deck, a post-tensioned concrete and steel composite structure, was constructed in segments using balanced cantilever methods. Each deck segment was either precast off-site and transported by barge, or cast in place atop temporary platforms extending from the pylons. As the main span grew outward toward the center of the river, temporary stay cables were anchored into the pylons and attached to each newly added segment. These cables, arranged in a fan pattern, were tensioned precisely using hydraulic jacks to counteract gravitational sag and to distribute structural loads symmetrically across both sides of the pylon. The stay cables themselves consist of high-strength steel strands encased in corrosion-resistant sheathing, anchored into massive anchor blocks within the pylon shafts. Vibration dampers were installed at intervals to mitigate wind-induced oscillations and ensure long-term fatigue resistance. Behind the structural work, the installation of intelligent transportation systems, roadway lighting, drainage infrastructure, and barrier systems proceeded concurrently. A crucial aspect of the bridge's construction involved integrating border control and inspection facilities on both sides, meaning the project had to encompass not just the main span and approaches, but also expansive landside infrastructure. These included customs plazas, inspection booths, weigh-in motion sensors, and secondary screening areas, all built to exacting standards set by two national governments. Coordination across these parallel construction zones required synchronized project management, shared construction specifications, and harmonized safety and environmental protocols. Cross-border utility integration further complicated the process. Power, water, data, and fiber optic lines had to be laid in conduits embedded within the bridge deck, secured and protected against temperature fluctuations, dynamic load stress, and electromagnetic interference. Weather posed another challenge. Extreme temperature swings, high wind exposure during deck segment installation, and ice buildup along the river all required constant monitoring and adaptive construction scheduling. With a total length extending over a mile and traffic capacity tailored for future expansion, the Gordie Howe International Bridge is not simply a physical connection between two cities. It represents a structural embodiment of modern binational cooperation and the evolving science of long-span bridge engineering, where every bolt, cable, and foundation element plays a precise role in maintaining stability, durability, and flow across one of the continent's most critical commercial corridors. In tackling the extreme demands of spanning the Straits of Mackinac, a 5-mile wide, windswept channel where Lake Michigan and Lake Huron converge, the Mackinac Bridge project stands as a masterclass in long-span suspension bridge engineering. Designed to accommodate seismic movement, thermal expansion, gale force winds, and ice flows, the bridge required a foundation to finish approach that pushed the boundaries of mid-20th century civil engineering. Work began with the placement of massive caissons in the deep strait. These caissons, steel cylinders reaching down to bedrock, were sunk using a combination of pneumatic excavation and underwater blasting. Once in place, they were backfilled with tremie concrete to form the piers that would support the suspension towers. The towers themselves rise from these caissons and were assembled using high-tolerance riveted steel plates, lifted by derrick cranes mounted on temporary platforms. Due to the depth and water conditions, the foundation work took several seasons and required round-the-clock shifts with divers, dredgers, and engineers coordinating in tight, hazardous quarters. The twin suspension towers, over 500 feet tall, consist of welded steel box sections built segmentally. Each section was hoisted using cableways strung between temporary falsework and then precisely aligned and pinned. Once both towers reached full height, the construction team began spinning the main cables, a process that involved passing individual wires back and forth across the span using a spinning wheel, then compacting and binding the bundles into the final diameter. These cables were anchored into massive concrete anchor blocks at each end of the bridge, poured over bedrock and reinforced with thousands of tons of rebar to resist the horizontal forces imposed by the suspended roadway. With the main cable secured, vertical suspender cables were hung at set intervals and tensioned to support the weight of the roadway deck. The deck itself was constructed using steel trusses and orthotropic deck panels, lifted into place from barges using floating cranes and suspended from the cables using custom fabricated clamps. Expansion joints and rocker bearings were integrated into the deck structure to accommodate longitudinal movement caused by temperature variation and traffic loads. The bridge was designed to flex several feet in any direction, a dynamic capacity necessary to endure winter ice loads and summer thermal expansion. Wind tunnel testing and aerodynamic modeling informed the bridge's profile, which includes a narrow, open-grid center lane section that reduces wind resistance and allows air to pass through the deck. Wind dampers and tuned mass dampers were also considered in the design to mitigate oscillations during high wind events. Paint systems for the structural steel involved multiple layers, including zinc-rich primers and elastomeric coatings designed to withstand harsh lake effect environments and freeze-thaw cycles. Maintenance access was engineered into the bridge with catwalks, internal tower ladders, and inspection rail trolleys integrated into the superstructure. De-icing and runoff control systems were also embedded into the deck, including scupper drains and weather monitoring sensors that inform bridge operation decisions. Overlooking the Peace River in northeastern British Columbia, the Seikan Dam emerged as the third major hydroelectric development on this river, following the Wack Bennett and Peace Canyon Dams. Planning for this project involved decades of studies, regulatory reviews, and public consultation before actual construction began in the mid-2010s. Once approved, the first phase of construction focused on site clearing and access preparation. This entailed removing thousands of hectares of vegetation, felling trees, building new access roads, and reinforcing existing ones to accommodate the massive flow of equipment and personnel. Additionally, geotechnical investigations were carried out early to determine subsurface characteristics, which were critical for designing stable foundations in a valley known for its complex geological conditions. Foundation excavation proceeded next, with crews stripping away overburden to expose competent bedrock. This phase involved the use of heavy earth-moving equipment such as hydraulic excavators, bulldozers, and articulated dump trucks, operating on a meticulously choreographed schedule to avoid bottlenecks. Extensive rock bolting and grouting were performed to stabilize the slopes and ensure that water seepage through the foundation would remain within allowable limits. At the same time, river diversion tunnels were being bored through the north bank. These twin tunnels, each several hundred meters long and several meters in diameter, were lined with reinforced concrete and designed to carry the full volume of the Peace River during the dam's construction phase. Once river diversion was in place, the main earth-filled dam structure began to take form. This embankment-type dam required the placement of millions of cubic meters of material in zoned layers, each serving a specific structural or impermeable function. The dam's core consisted of compacted clay designed to be nearly watertight, while the outer shells were built from gravel and rockfill for strength and stability. These layers had to be placed with extreme precision, both in terms of moisture content and compaction density, using a fleet of high-capacity vibratory rollers and GPS-guided dozers. Simultaneously, the powerhouse and spillway complex were under construction on the left bank. These concrete structures demanded an entirely different set of construction techniques, beginning with the erection of massive cofferdams to dewater the work area. Tremie concrete was often used for underwater placements, while large tower cranes and high-capacity formwork systems enabled continuous vertical construction. The powerhouse was designed to house 6 large Francis-type turbine generator units, each requiring massive steel components that were fabricated off-site and transported in modules. Beyond the physical structures, a network of transmission lines was installed to carry the electricity generated at Site C to the provincial grid. These high-voltage lines required the erection of steel lattice towers across challenging terrain with careful coordination to avoid environmental and cultural sensitivities. Environmental mitigation was a persistent theme across all stages of the project, involving fish habitat reconstruction, wildlife corridor planning, and ongoing monitoring of water quality and sediment levels. Any given day, the Hampton Roads Bridge Tunnel serves as a critical artery for transportation in southeastern Virginia, and expanding this corridor demanded an engineering response of significant scale and complexity. Initiated to alleviate chronic congestion and prepare for growing regional demand, the expansion focused not only on capacity improvement, but also on increasing structural resilience, environmental sensitivity, and long-term operational reliability. The keystone of the project involved the construction of a new twin-tube bored tunnel under the Thimble Shoal Channel, an endeavour that introduced tunnel boring technology to a region traditionally reliant on immersed tube methods. Site preparation began with extensive marine surveying, geotechnical borings, and environmental studies to ensure that dredging, pile driving, and excavation would proceed without destabilizing the existing infrastructure or causing adverse ecological impacts. This was followed by the mobilization of massive temporary trestles and staging areas built along the edges of the Hampton Roads waterway, where precast elements, equipment, and construction materials could be stored and deployed efficiently. Floating equipment such as crane barges, tugboats, and supply vessels formed a coordinated logistics network, essential for moving large-scale items such as precast tunnel lining segments and rebar cages to the offshore tunnel portals. The new tunnels, constructed using a tunnel boring machine specifically designed for the unique soil and hydrostatic conditions of the region, began with the launch pit on one side of the channel. The TBM was assembled on site in a specially excavated pit lined with slurry walls and reinforced with steel bracing. As the TBM advanced, it excavated through layers of clay, silt, and sand, simultaneously installing precast concrete segmental linings to form the circular tunnel structure. Each segment was set in place using hydraulic arms with gaskets to ensure a watertight seal, and the annular space behind the lining was grouted to prevent settlement or water ingress. Parallel to the tunnel construction, bridge widening and interchange improvements on the approach roads were carried out. This required staged demolition and reconstruction of existing structures, new pile-supported bridge spans, and lane realignments. Precast, pre-stressed concrete girders were lifted into place using heavy lift cranes, and cast-in-place decks were poured using travelling formwork systems. The sequencing of this work had to be tightly coordinated with ongoing tunnel operations to avoid disruption to traffic and construction activities. Ventilation buildings, fire suppression systems, and emergency egress pathways were integrated into the tunnel design to meet stringent safety requirements. The mechanical and electrical fit-out included high-capacity jet fans, LED lighting arrays, and a suite of sensors and control systems connected to a centralized monitoring facility. Waterproofing, corrosion protection, and redundancy in utility lines were also built into the system to account for the harsh marine environment. Launched at the heart of a massive cross-border logistics corridor, between Detroit, Michigan, and Windsor, Ontario, the Gordie Howe International Bridge emerges as one of the most technically ambitious and strategically vital infrastructure projects in North America. Designed as a cable-stayed bridge with an unprecedented main span length for this type of crossing in North America, the structure addresses not only current transportation needs, but also anticipates decades of future commercial and passenger vehicle growth. What sets this project apart is the integration of border processing facilities on both ends, a multi-use path for non-motorized users, and a focus on minimizing environmental impact during construction. Construction of the bridge began with an intensive ground improvement phase. On both the Canadian and American sides, the project required deep foundation stabilization due to soft soils and industrial legacy conditions. Thousands of concrete-filled steel piles were driven deep into the ground, many over 150 feet long, to support the massive load of the main pylons and approach structures. Vibrocompaction and dynamic replacement techniques were also applied in select areas to densify weak soils and ensure long-term settlement control. The signature feature of the bridge is its cable-stayed main span, which stretches more than 2,500 feet across the Detroit River. The two massive towers, each rising nearly 150 meters above the water, were constructed using climbing formwork systems with high-strength reinforced concrete placed in lifts and allowed to cure under strictly controlled environmental conditions. Each lift required careful coordination of embedded rebar cages, conduit for internal inspection systems, and multiple layers of quality control for alignment and geometric accuracy. The stay cables are arranged in a semi-fan pattern and connect to a composite steel concrete deck that is fabricated in modular segments. These segments are lifted into position by strand-jacking gantries placed atop the towers, and then post-tensioned into place as the structure progresses outward from both pylons in a balanced cantilever method. Because of the immense forces involved, cable anchorage zones in the deck were heavily reinforced and constructed using high-performance concrete to prevent cracking and fatigue over the bridge's lifespan. In parallel with the main span construction, the approach structures required extensive use of precast girders and segmental concrete box girders, supported on piers founded on deep drilled shafts and pile caps. Each approach segment had to be aligned precisely with the main span geometry to allow seamless connection once the cantilevers met at mid-span. Expansion joints, seismic isolation bearings, and cable dampers were installed to accommodate temperature changes, traffic vibrations, and potential wind-induced oscillations. Perhaps one of the most unique aspects of the Gordie Howe International Bridge is the inclusion of full customs and inspection plazas on both sides of the river, which had to be constructed concurrently with the bridge. These facilities involve complex building systems, large-scale pavement infrastructure, and real-time data integration with transportation networks. Stormwater management, energy efficiency, and border security technologies were embedded into their design from the outset. There are few engineering feats that match the complexity and precision required to lift a functioning roadway within an existing bridge arch, all while keeping maritime and vehicular traffic moving. The Bayonne Bridge, Raise the Roadway project was exactly that kind of endeavor, a surgical transformation of a legacy structure to meet the demands of modern commerce. Originally opened in 1931, the Steel Arch Bridge connecting Bayonne, New Jersey to Staten Island, New York had a vertical clearance insufficient for newer Panamax and post-Panamax container ships to pass beneath. Rather than demolish and rebuild, the project team pursued an extraordinary solution. Raise the roadway from its original elevation to a new, higher level, without altering the historic arch. The operation began with extensive structural assessments of the existing steel arch, whose riveted trusses were still in remarkably good condition. The original roadway deck, hung from vertical suspender cables connected to the arch's underside. These suspender cables were gradually unloaded as crews prepared for the insertion of an entirely new deck system, this time supported above the old roadway and suspended higher within the arch span. Construction began with the fabrication of steel support columns and crossbeams anchored to the existing arch ribs. These temporary and permanent steel components were staged off-site and moved into place with extreme logistical care, as space was limited and much of the work had to be performed from barges or scaffolding. A critical step involved the staged demolition of sections of the original roadway, which were removed incrementally while traffic continued on other lanes. The demolition had to avoid disturbing the live structural behavior of the arch, meaning that counterweights, temporary supports, and load redistribution were all carefully engineered for each phase. After the initial segments were cleared, the new roadway deck segments were installed section by section, elevated well above the original deck level. These new segments utilized orthotropic steel panels with welded ribs to minimize weight while maximizing stiffness, allowing for long spans between vertical supports. To complete the transition, the team had to construct new approach ramps on both sides of the river that gradually transitioned from the existing ground level to the newly elevated bridge deck. These approaches were supported by drilled shaft foundations and used cast-in-place concrete piers and precast girders. Each piece had to align precisely with the central span deck geometry to maintain smooth grade transitions and proper drainage slopes. One of the most impressive features of this project was the uninterrupted use of the bridge throughout much of the work. A movable, temporary trestle system allowed traffic to continue using the bridge, even as sections of the original deck were removed and replaced. This required careful scheduling, custom staging platforms, and constant monitoring of structural loads to avoid overstressing any part of the arch. Instead of dismantling an aging bridge and replacing it with a new one, engineers tasked with the Bayonne Bridge, Raise the Roadway project, chose an unprecedented path, building a higher roadway within the existing arch structure, all while keeping traffic flowing and preserving the historic character of the original span. This decision was driven largely by the need to accommodate the larger container ships enabled by the expansion of the Panama Canal. The original vertical clearance of the Bayonne Bridge, which stood at approximately 151 feet above mean high water, was no longer sufficient to support this new class of vessels accessing the Port of Newark and Port Elizabeth. Raising the clearance to nearly 215 feet became a logistical imperative. The existing bridge's steel arch, a landmark engineering structure from the early 20th century, presented both opportunities and limitations. Its structural integrity remained excellent, allowing it to be repurposed to support a new elevated roadway. The challenge was that the original deck hung from vertical suspenders below the arch's apex. To raise the roadway, engineers devised a complex method of constructing a new deck above the original without disrupting either maritime activity below or vehicular activity above more than absolutely necessary. The process began with the construction of a series of temporary support structures within the arch, allowing workers to access both the existing deck and the new construction zone above it. New piers and approach structures were simultaneously being constructed at both ends of the bridge using reinforced concrete columns supported on deep foundations, often drilled shafts socketed into bedrock. These approaches would eventually tie into the new elevated roadway. Once temporary supports were in place, workers began erecting steel framing for the new upper roadway within the arch span. This framing consisted of longitudinal girders and crossbeams bolted and welded into position, followed by installation of orthotropic deck panels. These panels were fabricated off-site and trucked in for precise placement, reducing on-site assembly time and improving quality control. The steel deck design provided a lightweight yet structurally robust solution that minimized additional loading on the arch. Throughout this process, extensive structural analysis was continuously performed to ensure that loads were properly transferred through the original arch structure. Sequencing was essential. As the new deck was installed section by section, old portions of the original deck were removed underneath in a carefully planned reverse progression. Traffic was maintained through the use of temporary roadways and weekend closures scheduled around critical lift and removal operations. Seismic upgrades, drainage improvements, lighting systems, and safety features were all integrated into the new deck, bringing the structure up to modern standards without compromising the visual profile of the historic arch. Once the elevated roadway was fully connected to the new approaches, the bridge could serve modern truck traffic and massive container ships alike, without ever having lost its central role in the region's infrastructure. Beneath the southern skyline of Portland, Oregon, the Sellwood Bridge replacement project unfolded as a carefully orchestrated effort to modernize a century-old crossing while respecting the constraints of an urban setting and a sensitive river environment. Originally opened in 1925, the existing structure had long been structurally deficient and functionally obsolete. It carried tens of thousands of vehicles per day on a narrow, deteriorating deck with no shoulders and minimal pedestrian accommodations. The new bridge would not only replace the failing structure, but also vastly improve safety, seismic resilience, and multimodal capacity. The design of the replacement bridge called for a deck arch structure which would span the Willamette River with minimal disruption to the waterway and surrounding neighborhoods. Prior to any new construction, engineers faced the unique challenge of what to do with the existing bridge. Instead of fully demolishing it up front, a temporary solution was implemented. The original steel truss was shifted laterally, intact, onto temporary piers constructed just downstream. This extraordinary lateral slide operation allowed the old bridge to remain in service while the new bridge was built in its original alignment. The lateral move required precise hydraulic jacking systems and heavy-duty rollers. Crews disconnected the truss from its existing piers and then slowly slid the entire structure onto a set of temporary supports built on drilled shafts. This move, executed in just a few hours after weeks of preparation, cleared the path for demolition of the original concrete piers, many of which had suffered extensive corrosion and were no longer structurally viable. With the original alignment clear, construction of the new bridge began with installation of deep foundation elements, including drilled shafts socketed into bedrock beneath the riverbed. These shafts would support the new reinforced concrete piers, which in turn carried the load of the deck arch. The arch segments were constructed using a balanced cantilever method, with concrete segments cast in place and post-tension to maintain structural integrity as they extended symmetrically from each side of the river. The bridge deck itself was cast in segments atop the arch ribs using a system of false work and custom-formed travelers. The deck accommodated 2 standard travel lanes in each direction, generous bike lanes, and wide sidewalks on both sides, features entirely absent from the original structure. In addition, the deck design included integrated stormwater treatment systems to capture and filter runoff before it entered the Willamette River. As the new bridge took shape, utilities were relocated, traffic patterns shifted, and seismic isolators were installed beneath critical components to provide flexibility in the event of an earthquake. Steel reinforcement was designed with corrosion resistance in mind, and all concrete elements were specified with admixtures tailored to the region's wet climate. Once the new structure was complete and fully operational, the old temporary bridge was dismantled and removed from its temporary supports. Final phases included landscaping, approach road improvements, and installation of aesthetic lighting and railing features to blend the bridge with its urban and natural context. As the rising arc of twin basket handle arch bridges took took shape over the Mississippi River, the transformation of the I-74 corridor between Bettendorf, Iowa, and Moline, Illinois, entered one of its most critical and technically ambitious phases. The construction of the new I-74 Mississippi River Bridge was not merely a replacement of aging infrastructure, it was a complete reimagining of regional connectivity, driven by modern standards for traffic volume, safety, and structural resilience. The original bridge system, composed of two separate spans constructed decades apart, had long been overcapacity and structurally obsolete, necessitating a solution that would carry 4 lanes of traffic in each direction, with substantial shoulders and multimodal accommodations. Foundation work for the main river crossing demanded meticulous geotechnical investigations due to the presence of complex riverbed conditions. Deep caissons and drilled shafts were deployed to reach competent rock, with many of the drilled shafts extending over 100 feet into the bedrock below the Mississippi's muddy floor. This phase involved the use of massive steel casing, oscillators, and reverse circulation drilling techniques to ensure shaft integrity in an environment challenged by underwater currents and variable sediment layers. Cofferdams were constructed to create dry working conditions for pier construction, each one engineered to resist the high hydrostatic pressures of the river during seasonal flooding. The signature basket handle arch design was selected for both aesthetic and structural performance. These arches rise more than 100 feet above the deck and were fabricated in large segments off-site, then transported by barge to the erection location. The erection sequence was tightly choreographed. Arch ribs were lifted and pinned using floating cranes during periods of calm river flow, with crews performing high elevation bolting and welding operations within tight tolerances. Each arch rib section was temporarily braced and connected via knuckle joints and box diaphragms until the entire arch structure was self-supporting. The steel itself was weathering grade, chosen to reduce long-term maintenance needs and withstand the extreme freeze-thaw cycles common to the upper Midwest. Suspended below each arch is a post-tensioned concrete deck carried by steel hangers arrayed in a vertical configuration. The bridge deck was cast in place, using a traveling formwork system that advanced span by span. Epoxy-coated rebar, high-performance concrete mixers, and continuous monitoring of curing conditions ensured long-term durability. Expansion joints were minimized through the use of integral abutments and deck continuity, reducing maintenance complexity. Parallel to the main river spans, approach structures on either side required extensive reconstruction and realignment of existing highway infrastructure. Mechanically stabilized earth walls and drilled shaft-supported piers form the backbone of the approaches. The coordination of traffic staging during construction was a major challenge, as portions of the existing bridge needed to remain in service throughout the process. Temporary crossovers, stage demolitions, and nighttime steel girder installations were part of a detailed traffic management strategy. Few infrastructure projects in the northeastern United States have so comprehensively redefined regional mobility as the construction of the Governor Mario M. Cuomo Bridge. Spanning the Hudson River between Tarrytown and Nyack, this modern twin-span structure replaced the aging Tappan Zee Bridge, which had served for over 6 decades but was increasingly unable to meet the demands of 21st century traffic, safety, and structural performance requirements. The replacement effort was not only monumental in scale, but also served as a showcase of accelerated design build execution, seismic resilience, and long-span cable-stayed bridge engineering. Construction began with an extensive program of pile driving and cofferdam installation in the river's soft glacial sediments. More than 1,000 piles were driven to create the foundations for the main span towers and approach piers, with many of them extending over 200 feet below the river surface to reach competent strata. These piles were either steel pipe piles or concrete-filled steel cylinders driven using high-capacity hydraulic hammers aboard floating barges. Each pile had to be carefully aligned to meet strict tolerances, and dynamic load testing was performed regularly to verify bearing capacity. Central to the structure are the cable-stayed main spans, each carrying 4 lanes of traffic with additional space for emergency shoulders and a shared use path. The twin main span towers, constructed with reinforced concrete, rise from pile-supported cofferdams and were built incrementally using jump-form systems. These towers house the anchorages for the stay cables, which are arranged in a semi-fan configuration and composed of galvanized steel strands enclosed in protective sheathing. Each cable was tensioned individually using strand jacks, and their load paths were continuously monitored throughout installation to maintain even deck camber and prevent distortion. The bridge's deck was constructed using precast concrete panels and structural steel girders. These panels were fabricated off-site and barged to the work zone, where they were lifted into place by gantry cranes and secured with high-strength post-tensioning systems. By utilizing modular construction, the project team reduced field labor intensity and maintained strict quality control over concrete finishes and rebar placement. Simultaneously, orthotropic deck sections were integrated into specific areas where weight savings were essential, particularly near the tower anchorages. Wind loads and thermal expansion across the bridge's more than 3-mile length were key design considerations. Expansion joints with built-in damping systems were installed at each abutment and tower transition. The bridge is also equipped with smart monitoring systems embedded within its structure, capable of measuring strain, tilt, temperature, and traffic load in real time. On the western span, a dedicated bicycle and pedestrian path was constructed, complete with belvederes for scenic viewing and interpretive signage. This element, though minor in structural weight, required careful coordination with the main deck construction to maintain alignment, loading distribution, and railing continuity. The lighting system was also integrated directly into the bridge structure, minimizing the need for maintenance access while providing full-spectrum LED visibility and programmable displays for special events. At the heart of the Link US Transit Corridors initiative is the task of transforming key transportation arteries in the Columbus, Ohio metropolitan region into high-capacity, multimodal corridors built for future urban growth. Unlike typical bus transit upgrades, the Link US program requires a comprehensive re-engineering of the roadway environment to support bus, rapid transit systems, pedestrian-focused infrastructure, and mixed-use urban development, all while preserving functionality for existing traffic and utility services. The first phase of physical work along a corridor typically involves relocation of utilities, both above and below ground. Electrical vaults, telecommunications ducts, gas lines, and water mains are mapped, protected, or moved to ensure that dedicated BRT lanes, new medians, and expanded sidewalks can be constructed without interference. In many cases, trenchless methods like horizontal directional drilling are employed to install new conduits beneath existing infrastructure with minimal surface disruption, particularly in dense commercial zones. Once the underground conflicts are cleared, road reconstruction begins. The new BRT lanes, often located in the center of the roadway, are built with reinforced concrete pavement sections designed for heavy axle loads and continuous operation. These lanes are separated from general traffic by raised curbs or delineators and incorporate mountable transitions at intersections to allow emergency access. Drainage patterns are revised through the addition of new catch basins, bioretention swales, and subsurface infiltration trenches, which both control runoff and improve stormwater quality. Platforms for BRT stations are constructed as raised, ADA-accessible boarding zones with tactile strips, real-time signage pylons, lighting, and weather shelters. Each station integrates with sidewalk improvements and signalized crosswalks, often requiring curb realignments and installation of new traffic signals with transit signal priority features. Median-based stations include special design considerations for pedestrian access, often requiring median refugees or fully protected intersection phases to ensure safe crossing movements. Beyond the roadway and platform work, the corridors also undergo significant landscape and urban design transformation. Utility pole removal, replacement of overhead wires with underground systems, and installation of street trees and furniture all contribute to a more pedestrian-oriented environment. Road diets are implemented in segments to reduce the number of general-purpose lanes, providing the right-of-way for wider sidewalks, cycle tracks, and designated turn lanes. These changes are reinforced with textured or colored pavement treatments at crosswalks and intersections to enhance visibility and reinforce multimodal priority. The Link US program also incorporates transit-oriented development zones adjacent to high ridership stops. Construction work in these areas involves coordination with private developers, staging of future utility corridors, and the preparation of building pads with coordinated grading and stormwater infrastructure. Each segment includes provisions for utilities and services. Rather than beginning at a central hub or urban terminal, the Alto High-Speed Rail project's earliest fieldwork concentrated on corridor preparation through rural and semi-rural regions, where right-of-way acquisition and grading could proceed with minimal disruption. The rail line, intended to connect Toronto to Quebec City with ultra-fast, electrified service, required the creation of an entirely new grade-separated alignment, distinct from the existing freight-heavy rail network. This demanded comprehensive land surveying, geotechnical assessments, and environmental clearances across hundreds of kilometres before any civil works could start. Once alignment studies and land procurement were finalised, the corridor was divided into construction segments managed by multiple contractors. Earthworks commenced almost simultaneously across numerous stretches, involving topsoil stripping, subgrade stabilisation, and extensive cut and fill operations. In some areas, embankments rose over 10 metres high to maintain consistent gradient profiles, while in others, deep rock cuts were blasted to maintain design speed tolerances. Where the route intersected natural waterways or wetlands, precast culverts and multi-span bridges were installed, with sediment control measures and wildlife passages integrated into the design. One of the most technically demanding aspects was the trackbed itself. High-speed rail demands extremely tight tolerances for vertical and horizontal alignment, necessitating a multi-layered track foundation system. Sub-ballast and ballast layers were placed over geotextile reinforced subgrades compacted to precise densities. In critical high-speed segments, especially on long straightaways or gentle curves, slab track systems were used instead of ballast, incorporating precast concrete panels anchored to reinforced concrete bases. These sections offered better long-term stability and reduced maintenance frequency, essential for sustaining speeds approaching 300 kilometers per hour. Electrification followed closely behind track installation. Overhead, catenary systems were constructed using regularly spaced mass, tensioning assemblies, and contact wire supports calibrated to minimize sway and maintain constant contact with the pantograph. Substations were placed at strategic intervals to step down transmission voltage and feed it into the overhead system. These were built on elevated pads and connected to regional grids through buried or overhead transmission lines, depending on terrain and corridor width. Stations along the Alto line featured a combination of central platform and side platform configurations, with full-length canopies, soundproofed glass walls, and automatic platform screen doors. Structures were built using steel frames and precast concrete panels to accelerate construction schedules and standardize elements across cities. At major urban terminals, such as Montreal and Ottawa, new underground concourses and connection tunnels were excavated using a mix of cut and cover and tunnel boring techniques to integrate with existing transit networks. Control and signaling infrastructure represented a core component of the system's operational integrity. The Alto Line uses a European train control system adapted for Canadian conditions, relying on continuous communication between trains and trackside balises to manage speed, spacing, and braking curves. Fiber optic cables were laid alongside the right-of-way, bundled with power and data conduits in armored ducts, and routed through centralized equipment rooms for resilience and redundancy. Noise mitigation was essential throughout populated areas. This was addressed through the installation of acoustic barriers, vibration-isolated track beds, and embankment berms shaped to deflect sound. In addition, crossing eliminations were carried out at every road and rail interface, either through overpasses, underpasses, or full-grade separations, ensuring uninterrupted operation of the high-speed network. Set against the wide-open expanse of eastern Nevada, the Spring Valley Wind Farm was developed to capture the region's steady wind resources and convert them into utility-scale electrical power. Building such a facility began with a detailed wind resource assessment using meteorological towers to gather multi-year data on wind speed, direction, and turbulence intensity. This information guided the precise placement of each turbine to maximize efficiency while minimizing interference between units. Before installation could begin, the site underwent grading and road construction. Access roads had to be engineered for heavy transport loads, as turbine components, blades, towers, and nacelles are among the largest and heaviest pieces of equipment moved over land. The roads were designed with gentle curves and controlled gradients to accommodate the specialized trailers used for hauling blades that can span well over 100 feet in length. Foundations for each turbine required deep excavation to reach stable soil strata, followed by the placement of reinforced concrete pads. The circular foundations were heavily reinforced with steel rebar cages designed to resist overturning forces generated by wind loads on the tower. Anchor bolt assemblies were precisely positioned to match the base flange of the tower sections. After concrete placement, a curing period ensured that the foundation reached its full design strength before tower erection began. The tower installation process was conducted in segments, typically 3 to 4 cylindrical steel sections lifted into place by high-capacity crawler cranes. Precision alignment was critical, with each section bolted and tensioned to exact torque specifications. Once the tower was complete, the nacelle, housing the gearbox, generator, and control systems, was hoisted to the top. Blade installation was one of the most technically challenging steps, often requiring calm weather conditions for safety. Each blade was bolted to the hub, and the completed rotor assembly was lifted and attached to the nacelle's main shaft. Electrical cabling inside the tower connected the generator to underground power lines, which routed energy to a substation. At the substation, transformers stepped up the voltage for transmission over long distances, and control systems monitored the performance of each turbine in real time. Data from sensors on the nacelle and blades fed into a centralized control center, allowing operators to adjust blade pitch and yaw to optimize energy capture. When fully operational, the Spring Valley Wind Farm stood as a coordinated network of mechanical and electrical systems, engineered to operate reliably in the region's unique wind patterns and contribute clean, renewable power to Nevada's grid for decades to come. Situated from an engineering standpoint, Detroit Metropolitan Wayne County Airport is a layered composition of airfield systems, structural innovations, and transportation logistics brought together under one of the busiest aviation hubs in the Midwest. Its design and continual upgrades illustrate the demands of modern air travel on both infrastructure and operations, particularly in a four-season climate that presents snow, wind shear, and high summer heat. The layout of the airfield is dictated by a network of parallel and intersecting runways, each surfaced with high-strength Portland cement concrete capable of supporting repeated impact loads from wide-body aircraft. These runways are underlain with aggregate-based courses and treated subgrades to mitigate frost heave and subsurface water migration. Embedded within each runway and taxiway are systems for runway lighting, electrical cable ducts, and aircraft guidance signs. Engineers incorporated FAA standard grooving on runway surfaces to improve water drainage and reduce hydroplaning risk, a critical detail in airport pavement construction. The terminals themselves are multi-story steel and concrete structures anchored by deep pile foundations. These piles extend below the frost line and into stable soil strata, designed to distribute vertical loads from the concourses and jet bridges. Each terminal is framed using steel columns and wide flange beams with composite concrete floor decks, chosen for their high strength-to-weight ratio and ability to span large open areas like ticketing halls and baggage claim areas. The roofs are framed with long-span steel trusses that allow for open, column-free spaces in the concourse areas, maximizing circulation and passenger flow. The McNamara Terminal, one of the key expansions at the airport, features an automated people mover system running the length of its concourse. The guideway was constructed with precast concrete guide beams mounted on cast-in-place piers, incorporating seismic joints and expansion bearings to accommodate thermal movement and vibration. The vehicles operate on a cable pull system embedded within the guideway, with control systems synchronized to station gates to optimize dwell times and passenger throughput. Beneath the passenger terminals lie extensive baggage handling systems, high-speed conveyors, diverters, and scanning units routed through multiple levels and security checkpoints. Mechanical engineers coordinated ductwork, fire suppression piping, and electrical conduit to share tight overhead spaces with baggage infrastructure, requiring three-dimensional coordination models and clash detection software during the design phase. Airside operations are supported by a fleet of underground utilities, including jet fuel hydrant systems, aircraft ground power units, and preconditioned air supply points. The hydrant fueling system was built with double-walled underground piping and leak detection monitoring, routed through trench boxes laid beneath the tarmac and connected to fuel farm distribution pumps at a remote site. Snow removal and de-icing are another critical infrastructure component. The airport includes heated pavement zones at gate positions, glycol collection systems with detention ponds, and airfield maintenance buildings equipped with vehicle staging, snowplow maintenance bays, and bulk material storage. Drainage systems are engineered to divert and treat de-icing fluids before discharge, ensuring compliance with environmental regulations. From the earliest stages of planning, the construction of the Venetian in Las Vegas was envisioned as both a large-scale hotel and a themed architectural reproduction of Venice's iconic landmarks, requiring careful integration of structural engineering with elaborate facade detailing. The project began with deep foundation work, as the sheer height and footprint of the resort demanded a robust support system. Pile foundations and reinforced concrete mat slabs were installed to distribute loads evenly across the variable desert subsoil, with strict tolerances to accommodate the superstructure's alignment. The main tower and podium levels were built using a reinforced concrete frame for strength and fire resistance, while structural steel was introduced in key areas to allow for larger spans and open interior spaces, particularly in the casino floor and grand lobby. This combination of materials provided both rigidity and flexibility in meeting design requirements. The building envelope had to be engineered to withstand the extreme heat of the Mojave Desert while supporting ornate architectural elements, stone cladding, decorative moldings, and replicas of Venetian arches and columns, without compromising structural integrity. Mechanical, electrical, and plumbing systems were integrated early in the superstructure phase to serve the massive volume of rooms, retail areas, restaurants, and entertainment venues. High-capacity HVAC systems were distributed through mechanical floors, with ductwork routed in concealed chases to maintain the interior's thematic authenticity. Plumbing networks were particularly complex, supporting not only the thousands of guest rooms, but also the extensive canal and fountain systems that define the property's public spaces. The Grand Canal itself required specialized water engineering. A reinforced concrete basin lined with waterproof membranes was constructed to hold the waterway, while concealed pumping and filtration systems kept the water clear and flowing. Load calculations for pedestrian bridges and canal-adjacent structures ensured both safety and the realistic aesthetic of Venetian streetscapes. Interior fit-out work was equally intricate. Large expanses of stone flooring, decorative plaster ceilings, and imported materials were installed with a combination of modern fastening methods and old-world craftsmanship techniques. Lighting systems were carefully tuned to highlight architectural details and simulate the soft ambiance of Venice, while still meeting safety illumination standards for a high-occupancy building. As the final stages progressed, the integration of themed architectural features with state-of-the-art hospitality infrastructure made the Venetian a unique challenge from an engineering standpoint. When completed, it stood not only as a luxury destination, but also as a highly complex, large-scale building system disguised beneath a meticulously crafted facade that captures the essence of its namesake city. Rather than originating from a single excavation point, the Ontario Line subway project in Toronto is unfolding simultaneously across multiple zones, each with distinct geotechnical profiles, construction constraints, and staging challenges. This complex, phased approach is dictated by the nature of the line itself, a hybrid system incorporating underground tunnels, surface-level alignments, and elevated guideways, all within a dense urban environment with deeply entrenched infrastructure. The underground segments begin with launch shaft construction, typically established in large open-cut excavations. These shafts are stabilized with secant pile walls or soldier pile and lagging systems, supported by steel struts or tiebacks to resist lateral soil pressures. Excavation descends in stages to reach the tunnel invert elevation, where tunnel boring machines are then assembled and launched. Each TBM is equipped with an earth pressure balance or slurry shield, depending on soil conditions, allowing it to navigate soft soils, mixed face conditions, and glacial till while maintaining face stability. Tunnel lining is performed immediately behind the TBM's cutting head using precast concrete segments. These segments are gasketed and bolted to form a watertight ring, which becomes part of the permanent tunnel structure. The logistics of segment delivery, spoil removal, and TBM maintenance are coordinated from surface-level support sites, which include slurry processing plants, muck storage, and concrete casting yards. At intermodal stations like Exhibition, Osgood, and Queen, massive excavation pits are established using a top-down or cut-and-cover method. These stations interface with existing subway lines and utility corridors, necessitating complex underpinning of adjacent buildings, and the use of ground freezing or jet grouting to control groundwater inflow. Temporary decking allows surface roads to remain operational while deep excavation continues below. Internal strutting systems are critical to maintain the integrity of the excavation, particularly for multi-level station boxes with mechanical, ventilation, and emergency egress spaces. Above ground, elevated guideways are constructed using precast segmental construction or cast-in-place concrete methods. These viaducts require column piers with deep foundations, often drilled caissons or driven piles, to ensure stability in areas with compressible soils or fluctuating groundwater. Segments are lifted using launching gantries or segment lifters, then post-tensioned together to form continuous spans. Alignment tolerances are extremely tight to maintain ride quality and track geometry. Track installation across the entire line incorporates both direct fixation systems and traditional ballast and tie methods, depending on location. In tunnels, low-vibration track slabs are installed using high-strength concrete over a waterproofed base. Track work includes rail anchors, expansion joints, and insulated rail fasteners, all designed to meet noise, vibration, and thermal movement requirements. A substantial portion of the Ontario Line's complexity comes from its integration with live transit corridors, roadways, and utility networks. This involves ongoing utility relocations, including water mains, high-voltage cables, and telecommunications lines, all done with extensive traffic staging and night shifts to reduce surface disruptions. Monitoring of existing structures is continuous, using inclinometers, strain gauges, and real-time survey systems to detect any movement induced by construction activities. Rather than beginning with earthwork or bridge segments, the Patullo Bridge replacement project was first shaped by how it had to coexist with the structure it was replacing. The original bridge, a narrow steel truss span opened in 1937, needed to remain operational throughout construction. This imposed significant constraints on staging, alignment, and work zone safety, requiring meticulous sequencing and traffic management planning from the outset. The new bridge was aligned slightly upstream to minimize interference, allowing major works to proceed in parallel with live traffic. The new crossing was designed as a modern 4-lane cable-stayed bridge with provisions for eventual expansion to 6 lanes. Foundation construction began with installation of deep drilled shafts and large diameter caissons sunk into the riverbed. These elements, some exceeding 2 meters in diameter and extending dozens of meters into the underlying strata, formed the base of the bridge's main tower piers. Working in the Fraser River's dynamic flow regime meant cofferdams and silt curtains had to be used extensively to manage turbidity, prevent sediment transport, and protect aquatic habitat during pile installation and excavation. Above the waterline, the main towers were cast incrementally using climbing formwork systems. Each tower leg was built in a series of lifts, reinforced with dense rebar cages and post-tensioned anchors to resist the immense tension forces from the stay cables. These vertical elements were built with ultra-high performance concrete mixes tailored for marine exposure, freeze-thaw durability, and long-term strength gain. Cable installation followed a balanced cantilever method, where stay cables were added symmetrically from each tower to support segments of the bridge deck as they were assembled. The deck segments themselves were prefabricated off-site and barged to the location, then lifted into position using floating cranes and strand jacks mounted on temporary erection towers. As each segment was placed, its corresponding pair of cables was tensioned to support the dead load and ensure proper geometric alignment. The approach spans utilized a combination of precast and cast-in-place concrete girders supported by pile caps and column piers. These sections included integrated infrastructure for lighting, drainage, and utilities. Beneath the deck, seismic isolation bearings and expansion joints were installed to accommodate both temperature movement and earthquake-induced displacements, which were particularly important given the region's seismic profile. On land, extensive roadway realignment was undertaken on both ends of the bridge. This included new interchanges, elevated ramps, and pedestrian pathways. Utilities had to be relocated in coordination with multiple agencies, and temporary detours were constructed to keep traffic flowing during tie-in phases. Intelligent transportation systems were also built into the new alignment, including dynamic signage, cameras, and automated incident detection. A major feature of the new bridge was the incorporation of separated paths for cyclists and pedestrians, physically divided from vehicle lanes by barriers and raised decks. These facilities were not just add-ons, but integrated from the structural design phase, with loads, wind effects, and vibration behavior considered during the modeling of the full bridge system. Like the Puget Sound Gateway involves more than just building new roadways. It is about stitching together ports, distribution centers, industrial zones, and population centers with a network designed to withstand decades of growth and geotechnical complexity. The program hinges on completing 2 major corridor extensions, State Route 167 to the Port of Tacoma and State Route 509 to the Seattle-Tacoma International Airport area. These aren't simple highway extensions. They are multifaceted infrastructure systems woven through dense urban fabrics, environmentally sensitive zones, and active logistics corridors. The foundational effort began with extensive right-of-way acquisition, including dozens of industrial parcels, commercial lots, and sections of public land. Site clearing and demolition work had to be carefully sequenced to ensure active businesses and transportation flows weren't unduly disrupted. In many areas, phased demolition and temporary access roads were used to maintain traffic and construction staging efficiency. Once the sites were cleared, earthwork operations commenced with mass excavation, grading, and fill operations to establish the subgrade profiles for the new alignments. These activities often encountered unstable soils, particularly in areas near water bodies and wetlands, necessitating ground improvement methods such as stone columns, surcharge embankments, and wick drains to accelerate consolidation and avoid long-term settlement. Bridges form a central component of the Puget Sound Gateway's design, given the number of water crossings, rail corridors, and urban arterials the new routes must span. Structural systems varied by location. Some employed pre-tensioned concrete girders, while others utilized steel box girders to achieve longer spans or accommodate vertical clearance constraints. Foundations for these bridges were built using large-diameter drilled shafts socketed into glacial till or bedrock, with temporary casings and slurry techniques used where groundwater intrusion was significant. False work systems were installed with minimal encroachment on adjacent rail and road corridors, often during tight nighttime closures, coordinated months in advance. Stormwater infrastructure was a major focus throughout the corridor. Given the region's high rainfall and environmental sensitivity, advanced drainage systems were installed, including biofiltration swales, detention vaults, and oil water separators. In several segments, retrofits were made to older outfalls to meet updated stormwater discharge criteria. To further offset environmental impacts, the program incorporated significant wetland mitigation and stream restoration work. This included regrading stream beds, planting native vegetation, and installing fish-passable culverts to enhance salmon habitat connectivity. The roadways themselves were built with high modulus asphalt pavement sections capable of handling repeated heavy truckloads. Base layers were constructed using crushed aggregate wrapped in geotextile fabric to separate the subgrade from the structural layers. Intelligent transportation systems were installed throughout the new corridor sections, with fiber optic cabling laid in trench alongside the roadbeds to support variable message signs, CCTV, incident detection, and traffic management. Logistics were further complicated by the need to interface with ongoing freight rail operations and existing intermodal yards. Coordination with railroads was critical, especially during the construction of new overpasses and underpasses, where flagging operations, temporary shoring, and phased construction minimized service interruptions. Few infrastructure projects in the Northeast Corridor combined century-old obsolescence with 21st century engineering demands. Rail of Sound Transit 3 demands a construction strategy that spans decades, integrates multiple jurisdictions, and aligns civil, systems, and structural engineering disciplines across a vast and varied geography. This voter-approved expansion of regional transit infrastructure in the Puget Sound area includes new light rail lines, commuter rail improvements, and bus rapid transit corridors, all designed to accommodate a rapidly growing metropolitan population and its shifting transportation needs. At the core of Sound Transit, 3's physical execution is the construction of hundreds of miles of new guideway, some elevated, some underground, and others at grade, depending on topographic and urban constraints. In urban centers like Seattle, tunneling is a dominant component, requiring the use of tunnel boring machines launched from deep access shafts. These shafts are constructed using secant, pile, or diaphragm wall methods, followed by excavation and concrete base slabs to support TBM assembly. As each tunnel progresses, precast segmental lining is installed immediately behind the cutter head, and grout is injected into the annular space to stabilize the ground and ensure water tightness. In suburban and exurban areas, elevated guideways are more cost-effective and less disruptive. These are constructed using precast, segmental box girders, supported on piers founded on drilled shafts or driven piles. Span-by-span erection methods, including balanced cantilever or launching gantries, are used to minimize construction footprint and expedite the schedule. Each pier is precision-aligned to maintain track geometry, and expansion joints are incorporated to account for thermal movement and seismic activity, critical factors in the seismically active Pacific Northwest. At-grade sections, while more straightforward to build, require extensive utility coordination, signal integration, and roadway modifications. Track slab construction includes sub-ballast, geotextile membranes, and continuous welded rail affixed with elastomeric fasteners for noise and vibration control. Crossings at intersections include embedded track panels and are integrated with intelligent transportation systems for preemption and safety. Station construction across the Sound Transit 3 network varies by location and function. Urban stations often require deep excavation and support of excavation systems such as soldier piles and lagging or secant piles. Platform construction includes structural slabs, canopy systems, tactile guidance elements, vertical circulation components such as elevators and escalators, and integrated fare control areas. Suburban and elevated stations are typically built on structural steel or precast concrete platforms, allowing for faster modular assembly. Mechanical and electrical systems, ventilation, fire suppression, power distribution, and communications are standardized across the network but require bespoke design at each site to accommodate geography and usage. Overhead contact systems for power delivery are strung on catenary poles or integrated into tunnel soffits using rigid conductor bars. Signaling systems use automatic train control with centralized monitoring and dispatch centers, all fiber connected through continuous cabling installed alongside track or in dedicated utility conduits. The Sound Transit 3 program is being delivered in carefully sequenced phases, with each segment undergoing planning, environmental clearance, design, procurement, and construction on overlapping timelines. Coordination with local utilities, city planning departments, and environmental agencies is ongoing throughout the life cycle. Simultaneously, worksite safety, noise control, and public interface management are embedded into each contract package to minimize community disruption. Transforming